How does a star's mass quietly decide its fate? A gentle ember or a violent supernova? Why is iron the final element a star can forge? And how does it seal the star's doom? What hidden drama unfolds inside a star, while its outward glow seems calm and steady? Imagine drifting through vast cosmic clouds, where stars are born in quiet, misty nurseries. In these dark, interstellar clouds, vast and deep, gas and dust swirl silently. Gravity gently draws the particles together into dense pockets. Over eons, these pockets collapse and heat up. Then, one by one, tiny flickers of light ignite at their centers. Baby stars taking shape. These star seeds grow in size and warmth, nurtured by the gentle pressure of the cloud around them, until at last they shine through the darkness. Each newborn star emerges from its cradle slowly, like a gentle glow in the silent universe. Clusters of stars sparkle to life together, born from the same vast cloud, forming cosmic communities where once there was only dust. Looking through powerful telescopes, these clouds often appear as enormous pillars or castles of gas, softly illuminated from within by infant stars, like cosmic cathedrals built for new generations of light. This is the hidden lullaby of creation, where quiet forces gather to begin a new chapter in the sky. In these stellar nurseries, not all seeds grow the same. Some of these infant stars will gather extraordinary weight, budding into mighty giants, while others will remain smaller and gentler, glowing softly through the eons. It is as if the clouds themselves whisper that each star's future is written in the heft it carries. Deep inside each star, an unseen factor holds the power of destiny: the star's mass. A star bursting with mass carries a tremendous weight in its heart, pulling its core into fiercely high pressure and temperature. This makes massive stars burn their fuel faster, shining brighter but living shorter lives. Smaller stars, by contrast, glow more softly and serenely, conserving their energy and living far longer. Our own sun, humble and tranquil, will someday swell into a gentle giant and then fade quietly. It is far too small to ever explode. Only stars, with roughly 8 times the sun's mass, or more, can gather the strength for a supernova. Those heavy stars forge elements that smaller stars never can. And in the end, gravity may win a spectacular showdown. The true cosmic fireworks are reserved for the most colossal stars. For the less massive stars, the finale is far more serene. They drift their remaining outer layers into space like soft petals falling away, leaving behind only a faint ember of hot gas. Their worn-out cores become small, dim jewels that persist in quiet solitude for billions of years. The true cosmic fireworks, the grand supernovae, are reserved for the most colossal stars alone. In the hush of space, mass is the arbiter of destiny. It whispers to each star whether its end will be a gentle setting sun or a dazzling supernova. Here, in the boundless dark, the weight of starlight itself decides the path ahead. Now, let us drift into the heart of a star, where unimaginable fires burn. All that twinkles softly in the night owes its glow to this gentle fusion flame hidden inside each star. In the core, hydrogen atoms fuse together in delicate dances, combining into helium and releasing a warmth and light that flows outward. This fiery process is steady and gentle. It is the star's secret breath, the pulse that keeps it alive. Each tiny fusion event is quiet, yet in the billions they create the glimmer that we see on clear nights, a soft glow born of atomic longing. For many millions of years, the star will shine steadily on this fuel, marking the longest and calmest chapter of its life. For stars heavy enough, the story continues onward. When the hydrogen fuel in the core begins to run low, the core shrinks and heats until a new fire begins. Helium atoms combining into carbon. In this phase, helium atoms fuse, and the core glows even more fiercely as carbon and oxygen are born. The star's interior shines hotter in this second stage, yet it remains deceptively calm from the outside. Like turning to a fresh page, the star writes a new chapter in its luminous history, forging heavier elements as it gently burns through its store of fuel. From afar, the star's light might hardly flicker, but inside the core has become a blazing crucible of heavier fuel. Each burning chapter writes a new chemical signature. Helium yields carbon, carbon leads to oxygen, and oxygen to neon and beyond. With each stage, the star's core grows hotter, denser, and more restless, even as the star's outer light might seem steady. The fusion fire, once a gentle glow, intensifies quietly in the depths. Still, all is tranquil on the surface. To the eye, the star glows with serene brilliance, hiding the fiery forge within. Each stage of fusion feeds the star's gentle balance against gravity. So long as the core burns, the star remains stable, and the cosmos remains calm around it. But these times of burning are numbered. With every new element forged, the star steps closer to a fate that awaits beyond the fire. As the fuel in each layer dwindles, the star's final destiny comes closer, step by steady step, with every flicker of flame. Time passes, and the star enters the quiet build-up of its final years. In the core, heavier elements begin to ignite one after another, each in its own inner sanctum. Imagine the star like a cosmic onion, with each shell burning a different fuel around the growing core. Outside burns hydrogen. Inside that, helium glows. Then shells of carbon, neon, oxygen, and silicon light up as stages unfold deep within. Each successive layer burns hotter than the last, reaching incredible temperatures deep in the star's heart. With each new layer that begins to burn, the clock speeds up. What once took millions of years now takes far less time. Helium burns for mere eons compared to hydrogen's long life. Heavier fuels flame up and fade away in just centuries, years, or even months. This final construction proceeds in hushed intensity. Each layer ignites swiftly and exhausts its supply, adding its weight to the core and stirring the pressure upward. In the largest stars, the final silicon burning stage may last only days, more a bright flash than a chapter in the star's story. Every heavy element, from the carbon of life to the calcium in stone, is born in these cosmic furnaces long before it escapes into space. Yet here, in the quiet heart of this star, all of that creation remains locked inside, secret and still for now. All these treasures lie hidden, waiting for the day they will be scattered across the cosmos by a great event. All this time, the star's layers are building an immense weight at the core, yet from the outside, it may appear steady. Within, pressures are climbing. Each new fusion adds mass and pushes the core closer to its limits. It is quiet and still to observers, but deep inside, tension grows. The star, like a dancer on a high wire, maintains a fragile balance as the elements stack quietly around its center. At last, an iron heart settles at the core, too heavy to lift, too inert to burn. Iron, the heaviest treasure a star can forge, cannot give up energy through fusion. It has piled itself on quietly, like a stone heart deep inside. This iron core grows heavier and heavier, held up by strange forces. But the end is nearing. The star has built a heart it cannot hold forever. Now the star stands in a reverent hush, its iron core brimming with potential energy, but offering none. The great weight of iron presses inward, and the core is held up only by quantum forces and pressure, balanced on a knife's edge. Outside, the star may still glow steadily, but inside, the equilibrium is fragile. The universe seems to pause and wait, as if expecting what comes next. It is here, in this tense stillness, that destiny hangs. The star has made its iron heart by slowly burning every other fuel. Now, with no more fusion to prop it up, the core is a silent but hungry mass of iron. One day, a last inner layer of iron, or the slightest weakening, will cause the supports to give way. It might happen quietly, or in the turning of a single breath of energy, but it will surely happen. For a moment, even time itself seems to slow and whisper, as if the universe is listening for the star's last breath. In the vast calm of space, the star seems to sleep. It shines on, unaware of the turmoil stirring within. Yet within, a storm is gathering strength, held at bay by a fine thread. This is the threshold. The star's last breath has passed, and what follows will change everything. For now, though, it is still, standing on the brink of transformation. It is as if the universe itself holds its breath. The star remains at the edge of change, lingering in silence as it awaits its cosmic destiny. All around, the cosmos is still, as if waiting for the final act to begin. The silence is profound, pregnant with the expectation of the epic event to come. In the silent depths of a dying star, gravity quietly begins its final conquest. For an external observer, the star's surface may seem unchanged, yet at its core, an unstoppable process has begun. For millions of years, the star's core sustained itself through nuclear fusion, shining brightly. But now, in the last breaths of its life, the core has become an iron heart, incapable of fueling any more fusion reactions. This change is subtle and profound, largely hidden from view, yet crucial to the star's fate. As the core grows heavier through the ash of previous reactions, it approaches a critical threshold known as the Chandrasekhar limit. Beyond this point, not even the quantum pressure of electrons, which once upheld the core against gravity, can hold it up any longer. In the stillness that follows, it is as though the star itself holds its breath, waiting for the inevitable to begin. At this point, the iron core's mass may already be multiple solar masses, packed into a volume no larger than Earth. At this point, the iron core's mass may already be multiple solar masses, packed into a volume no larger than Earth. Over eons, the star has been building layers like an onion, each forged by a previous fusion stage. Near the core, helium fusion once created carbon and oxygen. Deeper still, neon and silicon fused into even heavier elements. Finally, At the very center, an iron core has been assembled. Iron fusion is the end of the line. Fusing iron into heavier elements consumes energy instead of releasing it. When the core has become mostly iron, it can no longer generate the outward pressure needed to support the star. Even though the star's outer layers continue to burn and glow, at its center, the engines have effectively gone quiet. In that deep darkness, gravity reigns supreme. Inside the iron core, electrons fight gravity through a strange quantum pressure. Under normal conditions, this pressure can support the core, much like in a white dwarf star. It arises not from heat, but from quantum mechanics. Electrons are so densely packed that no two can occupy the same state. This degeneracy pressure holds back gravity, up to a point. If the core's mass grows beyond about 1.4 times the Sun's mass, even this ghostly pressure can no longer withstand gravity's pull. As the star continues fusing elements into iron, its core inching upward toward that critical weight, the tipping point draws near. Suddenly, with no margin left, the heart of the star gives way, and the collapse begins. For context, it is sobering to consider the timescales involved. This star may have burned steadily for tens of millions of years, yet its final downfall unfolds in just a few heartbeats. For the star, eons of stability give way to an instantaneous tragedy. To us, it seems miraculous, yet for the star, it is simply the moment of truth. When that critical limit is finally breached, collapse happens almost instantaneously. The core's material plunges inward under gravity, reaching speeds of thousands of kilometers per second. In just a fraction of a second, the star's dense iron center is compressed into an incredibly compact object, denser than an atomic nucleus. Temperatures in the core skyrocket into the billions of degrees, so hot that atomic nuclei themselves begin to fall apart. High-energy photons tear iron nuclei into helium and free protons and neutrons, a process called photodisintegration that absorbs energy and quickens the collapse. As the core compresses, electrons and protons are forced together, colliding and fusing into neutrons. Each such fusion event releases a neutrino. These trillions of neutrinos, initially trapped by the extreme density, carry away an immense amount of energy. Together, these processes turn the collapsing core into a roiling inferno of particles and neutrinos. The implosion happens on an almost unimaginable timescale. The entire core, perhaps the size of our planet, can collapse down to the size of a city in just a few hundred milliseconds. From our human perspective, this is faster than a blink of an eye. A massive ball of stellar material is suddenly funneled into an incredibly small volume. This speed is so great that it outpaces sound by a wide margin. The infall is supersonic within the star. Yet even in these few brief moments, the conditions inside reach extremes as high as those just after the Big Bang. Then, at a certain point in the collapse, the core's density exceeds that of an atomic nucleus. Here, the repulsive nuclear forces between neutrons become significant, suddenly stiffening the core. The innermost region rebounds and halts, effectively bouncing back the infalling material. For a fleeting moment, a nascent neutron star has formed at the center, an unimaginably dense ball of neutrons glowing with trapped heat. From this point on, the star's fate is sealed, and only the explosive finale remains. From the crushing heart, an invisible storm emerges, the birth of a flood of neutrinos. Trillions of these ghost-like particles are born as protons, and electrons merge to form neutrons in the core's collapse. They surge outward at nearly the speed of light, almost unhindered by the dense matter around them. These neutrinos are tiny messengers of tremendous energy, carrying away more than 90% of the gravitational collapse's power. Though almost weightless and invisible, these neutrinos carry incredible energy outward. Their collective rush plays a pivotal role in the explosion's dynamics. As they stream out, their rare interactions with the surrounding matter deposit heat that helps revive the star's shockwave. For a brief moment, even neutrinos cannot escape. The core is so dense that it forms a kind of neutrinosphere, a boundary layer from which neutrinos eventually emerge. Inside this core boundary, neutrinos scatter repeatedly, trapped by the extreme density. After just a few milliseconds, the center becomes less opaque, and a torrent of neutrinos is unleashed. This outward rush of neutrinos is so intense that it's like the star is momentarily glowing in neutrino light. Once free, the neutrinos flood out through the overlying layers of the star, similar to how the sun's light radiates into space, carrying energy away. These neutrinos are like advanced messengers for the cosmic event. In a rare astronomical event, observatories on Earth detected a faint ripple of neutrinos from a supernova hours before its light shone brightly in the sky. It was a startling confirmation of the theory. Neutrinos slip out first, carrying word of the explosion across the vast distances of space. For those who witnessed it, the neutrino burst was like a whisper of the star's demise, arriving long before the spectacular fireworks. This ghostly herald underscores just how dominant neutrinos are in a star's final moments, carrying the secrets of the collapse across the universe. Some of this neutrino energy goes on to fuel the explosion itself. As the neutrinos stream through the star's layers, a small fraction scatter off gas atoms, depositing heat. This neutrino heating behind the shock front injects new energy into the outward moving wave, helping it to keep ploughing through the star. Without this unseen boost, the shock might have stalled, and the star would not explode so dramatically. In effect, these neutrinos not only carry energy away, but also give back a vital kick to the explosion driving the star apart. Even after the shockwave has launched, the drama in the core is not yet over. The newly formed neutron star at the center is still blisteringly hot, and it continues to emit neutrinos in a fading afterglow. For tens of seconds, this newborn neutron star spews neutrinos into space, slowly cooling down as it finds its new equilibrium. During that time, this core is the brightest neutrino source in the universe. Only when the neutrino storm fades does the neutron star finally settle into a quieter life. Though the photon light of the explosion will arrive later, the neutrino signal stretches on in its own way, telling the tale of the star's innermost engine. Because neutrinos can escape the core so readily, astronomers consider them the ultimate messengers from a supernova. These ghostly particles reach Earth hours before any light from the explosion, bringing direct news of the star's final moments. By studying their properties, scientists can infer the conditions inside the collapsed core, something no telescope can see. In this sense, neutrinos allow us to peer through the curtains of the star's interior, bearing the imprint of the extreme environment at the moment of collapse. They are truly carriers of cosmic secrets, revealing the state of the newborn neutron star and the explosive energies at play. Within the chaotic core, something truly explosive is set into motion. As the inner core's collapse halts, it rebounds like a compressed spring suddenly released. This rebound launches an immense shockwave that races outward through the star at supersonic speed. Initially, it carries all the focused energy of the collapse and core bounce, moving through the star's material like a hurricane tearing through air. Just tens of kilometers from the center, It sweeps outward relentlessly, compressing and heating each layer in its path. It is this shock's tremendous force that will ultimately rip the star apart from within. As the shock races outward, it plows through each concentric shell of the star. It first collides with the iron and silicon layers, instantly heating them to extreme temperatures. In these heated layers, nuclear reactions briefly reignite. Protons and neutrons launched by the shock may capture onto nuclei in rapid succession, forging new heavy elements in mere moments. This is where some of the heaviest elements in nature, like gold, platinum, and uranium, can be created in the crucible of the explosion. Every shell the shock traverses is scorched and partly disassembled, yet each also receives a burst of new energy from the shock's passage. However, the shock soon encounters a major obstacle. Sweeping through the still-in-falling outer shells, it expends huge amounts of energy disintegrating heavy nuclei. This process eats up much of the shock's force and can cause it to stall. The core's neutrino flood then intervenes, depositing heat behind the shock and revitalizing its push. With this unseen help, the shock regains strength, transforming into a runaway tide of destruction. From this point on, nothing can stop it. The star's outer layers lie completely in its path. Finally, the shock reaches the star's outer surface and blasts into space. It violently ejects the star's outer layers, accelerating them to tens of thousands of kilometers per second. At that moment, the star truly tears itself apart, its material torn loose and driven into the cosmos. The shockwave continues outward, but much of its energy is now carried away in the expanding debris, which will form a glowing supernova remnant. At the center, the collapsed core now lives on as a neutron star. In even heavier stars, that core might instead become a black hole. Either way, the star's outer layers have been blown away to start a new chapter in their journey. The moment the shock breaks through the star's surface, a brilliant flash sweeps out into the universe. For a brief instant, the star's outer shell is ripped open, unleashing a burst of light and high-energy radiation. This shock breakout flash can include a surge of X-rays and ultraviolet light as the heated surface is exposed to space. For observers from afar, the star quickly transforms from invisible to extraordinarily bright. In just a few minutes, this newborn supernova can outshine all the stars in its own galaxy combined. For those moments, it is the brightest beacon in its galaxy. After the flash of breakout, the supernova settles into a powerful glow that lasts much longer. The expanding debris is still extremely hot, and it shines brightly at optical wavelengths. Radioactive elements created in the explosion now take over as the power source. Nickel-56, forged in the collapse, decays to cobalt-56 with a half-life of about 6 days. Then cobalt-56 decays to stable iron with a half-life of about 77 days. Each decay releases energy that heats the gas and powers the supernova's light. This radioactivity means the supernova's brightness can stay high for weeks or months. In fact, if such an explosion occurred in our own galaxy, it could become as bright as the moon, even visible in daylight. Only when the radioactive fuel is exhausted does the light finally fade away. The details of the light curve depend on what kind of star exploded. Some supernovae with thick hydrogen envelopes display a plateau. After the initial peak, their brightness holds nearly constant for a few weeks before dimming. Others, like those from white dwarf explosions, rise and fall more smoothly without a plateau. Type 1, a supernovae, which we will discuss later, tend to reach a consistent peak brightness and then follow a reproducible fading pattern. Astronomers learn about each explosion by studying these variations, reading the light curve like a fingerprint of the star's death. Yet this dramatic ending is not the only fate for stars. The cosmos exhibits a diversity of stellar deaths, each leaving its own mark. Some stars explode with hydrogen-rich envelopes intact, while others have shed their outer layers. In certain cases, an aging companion star plays a role. Astronomers classify supernovae into types to keep track of these differences, each with its own story and signature. By studying these types, scientists piece together the many ways stars can meet their end. Most massive stars end their lives by core collapse. But even here, nature offers variation. If a dying star still retains its hydrogen envelope, the collapse we described produces a Type II supernova. These typically come from red supergiants, massive stars that have burned all their fuel, yet kept their outer hydrogen intact. In these explosions, the hydrogen shows up in the spectrum and can cause a long plateau in the light curve, during which the brightness remains nearly constant. By contrast, if the star has lost its hydrogen before exploding, perhaps stripped away by powerful stellar winds or a binary companion, the supernova looks very different. With the hydrogen layer gone, the star's collapse may still occur, but the explosion is classified differently. When hydrogen is gone, but helium remains, astronomers call it a Type 1b. If helium is gone as well, it is a Type 1c. These stripped envelope explosions still result from core collapse, but they lack the hydrogen and helium signature in their light. Instead, their spectra carry the fingerprint of the star's exposed innards, revealing carbon, oxygen, and other heavier layers. Another path to a supernova comes from compact stars. In a binary system, a white dwarf can steal matter from its partner or collide with another white dwarf. If its mass creeps past the Chandrasekhar limit, carbon and oxygen at its center ignite in a runaway thermonuclear explosion. This is a Type 1, a supernova. The star explodes from within, not from gravitational collapse. The entire white dwarf is consumed by fusion, turning into iron, nickel, and other heavy elements, and nothing remains at the core. In this cosmic blast furnace, the star is obliterated in an instant. Because the physics of this explosion is fairly uniform, Type I supernovae reach a nearly standard peak brightness. Astronomers have used these stellar lighthouses as mile markers to measure cosmic distances. By comparing the known luminosity of a Type Ia to its observed brightness, scientists can gauge how far away the host galaxy is. This method led to one of the greatest discoveries in modern astronomy. The expansion of the universe is accelerating. Thus, exploding white dwarfs have told us something profound about the cosmos. Even in death, these stars shape the universe by creating heavy elements like iron and nickel, and by serving as beacons in space. In the universe, there are even stranger endings. Stars with truly enormous masses, perhaps over 100 times that of the Sun, can die in a runaway pair instability explosion. In these giants, the core becomes so hot that high-energy photons create electron-positron pairs, suddenly removing pressure support. This triggers a titanic fusion burst that completely unbinds the star. The result is an exceptionally bright explosion, and nothing is left behind at all. Other exotic cataclysms include the mergers of compact objects. When two neutron stars, or a neutron star and a black hole, spiral together, they collide violently and produce a kilonova, along with intense gravitational waves. Though the mechanism is different from an ordinary supernova, these events also dramatically reshape matter. They are the forges of the heaviest elements through rapid neutron capture processes. Even the merging of two white dwarfs can trigger a powerful flash if they detonate. Each of these endings, pair instability blasts, compact mergers, and more, adds to the richness of the universe's story. Every explosion or flare seeds space with new elements and light, laying the groundwork for future stars and planets. Even as we end one chapter of this star's life, the story of its legacy has only begun. The supernova's fading light and expanding debris will mix with the galaxy, seeding the cosmos with heavy elements. In the quiet aftermath, new stars and planets will one day form from these ashes. The star itself may be gone, but its echoes live on in the universe it helped shape, a promise that even in catastrophe, the cycle of cosmic creation continues. In the quiet aftermath of a star's final blaze of brilliance, a different kind of beauty emerges among the stars. A cloud of glowing dust and gas unfurls, drifting outward from the vanished star like ripples from a cosmic pond. The shock of the explosion has left behind an expanding shell of stellar debris hurtling through space. This ghostly shroud of gas and dust pushes outward into the darkness at extraordinary speeds, unseen ripples in the fabric of space. As it grows, the shell sweeps up the thin interstellar gas and scatters heavier elements far and wide. Slowly and silently it drifts, a swollen bubble of matter marking where the star once was, telling its story not in light, but in material form. Though there is no sound in the vacuum of space, the echo of that explosion is everywhere. The shock front moves through the cosmos like a silent thunderclap, pushing and compressing everything in its path. Inside this expanding shell, gases reach temperatures of millions of degrees and glow in X-ray light beyond our sight. The shock wave ahead of the ejector sweeps up diffuse clouds of hydrogen and helium, forming a powerful border between stellar remains and interstellar space. Behind this border, a reverse shock scours the ejected stellar material itself, heating it and revealing the star's hidden elements. The transformation is violent, yet graceful, as if the universe is shaping a new sculpture from the star's own ashes. The speed of that debris is staggering. Fragments of the original star are blasted outward at a significant fraction of the speed of light, tens of thousands of kilometers per second. At first, the expansion is almost unopposed, but gradually the shell slows as it sweeps up more gas. Over decades and centuries it grows, expanding by light years into the surrounding void. In a human lifetime, the remnant can outpace light itself at first, but as the surrounding medium thickens, it decelerates to a gliding drift. Despite this deceleration, the expanding shell can continue for hundreds or even thousands of years, before fading entirely into the cosmic background. Within the shrapnel are the heavy elements forged in the star's furnace. Iron, silicon, calcium, and even gold or uranium might be among the fragments carried on the blast. Each atom, now free from the star's gravity, riding outward in the debris, will seed future generations of stars and planets. Cosmic dust grains form in the cooling gas, each one a tiny emblem of the star's life and death. The shell may carry away more than a dozen times the mass of our sun, now strewn in a thin, expanding lacework across the galaxy. In that lacework, shocks will ignite and die and ignite again as the remnant evolves. Astronomers can actually watch these shells grow. We see them as glowing clouds of gas in telescopes tuned to different wavelengths of light. In optical light, supernova remnants often appear as wispy filaments or nebulous rings. In X-ray light, they are luminous as they heat the gas to millions of degrees. Every observation shows a shell-shaped outline, a boundary pushed outward by the explosion's initial kick. Over time, these outlines change shape slightly, influenced by bumps in the surrounding gas or by magnetic fields threading through space. And yet, even as the shell drifts farther from the explosion, it does not fade away quickly. Its glow persists, marking the site of the upheaval with light that lasts for generations. The afterimage of the blast remains visible even when the burst itself has long vanished from sight. This is the beginning of the next act, as the ghostly remnant turns its fierce energy into a gentle, enduring shimmer. We will soon witness how this silent cloud of debris can continue shining, a fading star that refuses to go quietly. The ghostly shroud left behind is still bright enough to catch our eyes. The expanding shell, ablaze with heated plasma, glows in many colors of light. Hydrogen atoms in the shell emit a gentle red glow, while oxygen and other elements contribute green and blue. This natural fireworks show can last hundreds or thousands of years after the star's death. To observers, the supernova remnant appears as a brilliant nebula, a glowing ring or cloud in the night sky. What was once an invisible explosion now paints the darkness with lingering light. The source of this light is the continuing energy of the explosion, gradually leaking out. Radioactive elements forged in the blast decay and release energy, heating the surrounding gas. In particular, isotopes like nickel-56 decay into cobalt and then iron, releasing gamma rays. These gamma rays collide with electrons in the gas, causing them to flash and glow. Meanwhile, the shock wave itself keeps rattling through the gas, heating it to millions of degrees. Thus, even centuries later, the shell radiates across the spectrum in optical, X-ray, and radio waves. One recent supernova remnant teaches us this lesson well. After a star exploded in a nearby galaxy in 1987, astronomers watched its debris glow for decades. A brilliant ring of light, shaped by gas flung out before the explosion, continued to brighten even decades after the initial flash. With each passing year, the remnant's light flickered and expanded, telling of shock waves colliding with clouds of gas. Even as the supernova itself became too faint to see, its remnant blazed on, like a candle slowly flickering in the dark. Telescopes saw this light in radio, visible, and X-ray bands, confirming that the death of a star truly leaves a long, luminous echo. Some remnants shine for an astonishingly long time. Famous supernova nebulae, like the Crab Nebula, have been glowing ever since the explosion was seen by skywatchers in the year 1054. That's almost 1,000 years of afterglow. Over these centuries, the nebula slowly expands and cools, but it never quite goes dark. Space telescopes still capture its glow in X-rays, while backyard astronomers can view its milky tendrils with amateur telescopes. Where a star once ended, a new sky decoration persists, visible across the galaxy as a reminder of past violence. Modern telescopes see these remnants as ghostly objects filled with wispy arcs and filaments. At radio wavelengths, remnants appear as diffuse bubbles of emission. In visible light, we see glowing filaments and clouds of glowing hydrogen and oxygen. X-ray telescopes reveal a hot interior, flickering with charged particles energized by the shocks. Each wavelength peels back a different layer of the remnant, telling a story about the composition, temperature, and magnetic fields inside. Together, these observations paint a full picture of a corpse illuminated from within. Beyond its soft glow, the remnant carries a force that continues to reshape space around it. The energy of the blast still roars on, silently sculpting clouds of gas light years away. Where the shockwave leads, it compresses and compresses, carving new patterns into the interstellar medium. It is as if the thunder of the explosion still echoes through the void, unseen but powerful. This ongoing cosmic influence prepares the stage for a final act of creation and destruction as the supernova's legacy echoes onward. The shockwaves from a supernova continue outward, even long after the light has faded. As these fronts sweep through space, they compress clouds of gas and dust, often igniting new stars in their wake. Imagine a vast, silent thunderclap rolling through a misty forest. Each blast of pressure rearranges the mist into new shapes, turning a calm evening into a sculpted scene. In space, the effect is similar. With each passing century, the supernova remnant reshapes the interstellar medium around it, creating cavities, filaments, and sometimes triggering star birth in neighboring clouds. These shockwaves also accelerate particles to incredible speeds. Electrons, protons, and ions, caught in the turbulent magnetic fields of the remnant, can reach nearly the speed of light. We call these accelerated particles cosmic rays, and they flood the galaxy. Invisible and ethereal, cosmic rays carry the memory of the explosion across light years of space. Occasionally, they collide with atoms on Earth, giving us a tiny whisper of that ancient thunder. Thus, even though supernova remnants are silent in sound, they echo through high-energy particles and radiation. As the shock plows onward, it gathers material into dense shells. These shells can become places of new birth. When a shockwave plows into a cool, quiet cloud of gas, it can compress the cloud until gravity wins and stars begin to form. So a supernova's death throes can plant the seeds of future suns. Sometimes we see newborn stars and clusters on the edges of old remnants, as if the exploded star offered a final gift to the cosmos. In this way, life is born out of death in the heavens. The expansion of the remnant also shapes the local magnetic fields in space. These fields grow tangled and strong in the wake of the shock. Charged particles spiral along these field lines, emitting radio waves that make some remnants appear as hazy circles in radio images. If the magnetic field lines are twisted into patterns, we see their influence in the filamentary structures of the nebula. Thus, in every direction, the remnant looks different, sculpted by invisible forces. It is a cosmic echo without sound, a thunder still imprinting its rhythm on the heavens. Even from the edge of a galaxy, the effect of these shockwaves can be seen. Astronomers have observed supernova remnants crashing into massive clouds and blowing cavities tens of light years across. Some explosions seem to carve out entire bubbles, leaving behind rings or voids in the interstellar gas. Elsewhere, clustered stars and gas appear to align along the border of a remnant, suggesting the shockwave pressured matter into new alignments. These observations reinforce the idea that the titanic burst of energy continues to influence space on grand scales. The soundless thunder of the supernova keeps whispering long after the initial boom. As remnants age and grow, they become familiar celestial patterns in the night sky. Generations of astronomers have come to recognize them by their shapes and colors. The ethereal structures created by supernovae add character and mystery to their constellations. When we look at these structures today, we are seeing the slow dance of debris that began centuries or millennia ago. Each one tells a story of both devastation and creation, captured in starlight. As the night sky fills with new patterns, we turn our gaze to some of the most famous examples. Some supernova remnants are so bright and distinct that they have become names and images in our catalogues. Perhaps the most famous is the Crab Nebula, a cosmic cloud of colour born from an explosion observed in the year 1054. Tonight, It appears as a cloudy patch in Taurus, but it is also a complex tangle of glowing filaments and bright knots. At its center lies a rapidly spinning neutron star, a pulsar, which drives the nebula's energy. Winds from this pulsar keep the remnant aglow, sending out wisps of charged gas that race outward at half the speed of light. In many telescopic images, the Crab Nebula looks like a flower blooming against the dark, an enduring monument to a long-past event. Other famous nebulae dot the Milky Way, each with its own character. The Veil Nebula in Cygnus is a ghostly filament stretching across half a degree of sky. It is the aftermath of a star that exploded around 10,000 years ago. The wispy threads of neon and oxygen trace out a three-dimensional shell that we view nearly edge-on. Each filament is a boundary of shock, softly glowing red and blue. Astronomers sometimes call it the Cygnus Loop, or the Cirrus Nebula, a delicate swirl of cosmic gauze left over from the violent blast. Cassiopeia's lost star, also known as Cassiopeia A, is another marvel. This compact remnant spans only a few arc-minutes, yet glows brilliantly in radio, optical, and X-ray light. It came from an explosion that likely lit up our skies around the year 1680, though people at the time did not notice it. Today, we can image its interior clumps of heated material, rich in elements like silicon and iron. Cassiopeia. A looks like a nearly symmetric ring of shards, an expanding shrapnel field seen face-on. It stands as a bright spot in the sky, reminding us of an explosion we missed, but the cosmos remembers. In the large Magellanic Cloud, outside our galaxy, sits SN 1987A's glowing remnant. Its characteristic ring still shines, now much brighter than in the first years after the explosion. The light has revealed multiple rings, as if the star had precast ripples in space before it died. Astronomers point Webb and Hubble telescopes at it, mapping dust clouds forming in the aftermath. It reminds us that a star's death can produce delicate new structures, almost like a stone creating ripples in a pond. Newborn dust grains in the remnant indicate that even as it breaks apart, it builds new worlds in microcosm. Even Tycho Brahe's supernova remnant is well known by astronomers. In the constellation Cassiopeia lies a faint shell called Tycho's SNR, from the star Tycho observed in 1572. In X-ray images it glows with rings and knots, marking where the explosion's fastest parts broke through. Likewise, Kepler's supernova remnant in Ophiuchus from 1604 is a dusty patch that slowly expands even now. Each of these historical remnants appears as a small but bright spot when viewed with modern telescopes, a signpost of an event that some people recorded long ago. Their beauty is subtle but real, seen best with instruments that can peer through the veils of gas. The night sky is full of such relics of ancient cataclysms. Some are named for patterns they resemble: the Jellyfish Nebula, the Heart Nebula. Others are simply catalogue numbers, but all share a common origin in a star's final breath. Some are hundreds of light years across by now, others still remain compact. Yet each one, in every galaxy and every epoch, reminds us how the cycle of stellar life continues. Long before telescopes or modern science, people turned their eyes to the sky and saw these wonders unfold. To ancient skywatchers, a new star would appear suddenly, shining brighter than any other, then fade away over months. These appearances were rare and alarming, often recorded as omens or marvels. We call these guest stars, and they were in fact supernovae. Their stories were written down by meticulous observers in China, Korea, Japan, and even in the Middle East and Europe. Hundreds of years later, we can match their stories to the nebulae we see today, bridging the gap between our time and theirs. One famous record comes from 1054 AD, when Chinese astronomers described a new star so bright that it was seen during the day. For nearly a month, it outshone every other star. That sighting was the supernova that created the Crab Nebula. They noted its appearance, its colour, and how it gradually faded over 2 years. Centuries later, astronomers identified a nebula in Taurus, about 6 light-years across, which we now know is the aftermath of that explosion. This link between written history and observable nebulae is one of the most direct connections we have to stellar death in the past. Another legendary guest star appears in records of 1006 AD. Observers in China, Japan, the Arab world, and Europe noted a brilliant star in the constellation Lupus that outshone all others. It was likely the brightest stellar event in recorded history, visible to the naked eye for nearly 3 years. This supernova, now called SN 1006, left behind a large, faint remnant, glowing today in X-rays and radio waves. Though it has dimmed far beyond naked eye visibility, astronomers can still spot its ghost with modern telescopes. The fact that observers wrote about it at the time gives us exact dates, helping scientists calibrate the story of that remnant's growth. In November 1572, Tycho Brahe witnessed a new star in Cassiopeia. This new star briefly rivaled Jupiter in brightness and defied the old beliefs that the heavens could never change. Tycho noted its position carefully. No nearby planet or moon could account for it. He found that this object had no parallax, showing it lay far beyond the moon, in the realm of stars themselves. We call it Tycho's supernova, and its faint, expanding remnant is visible today as a ghostly circle. It is known in radio wavelengths as well, but its birth was first recorded by the great astronomer Brahe and his contemporaries. The supernova of 1604, seen by Johannes Kepler and others, was the most recent one observed in our galaxy with naked eyes. It appeared in Ophiuchus and was observed from October 1604 onward. Kepler wrote a detailed treatise on it, noting how the new star rivaled Venus in brilliance at its peak. It slowly faded over a year until it was gone from sight. Its remnant, known as Kepler's SNR, can now only be seen with telescopes, glowing faintly as a shadow of that brilliant flash. Thus, for centuries, humanity has watched supernovae as rare surprises, marking them in chronicles as extraordinary celestial events. Today, when we see a glowing remnant, we carry the notes of those ancient skywatchers. The memories of light from bygone stars are etched in our historical records, and our telescopes often recognize the same positions. For example, the story from 1054 fits the Crab Nebula. 1572's star aligns with Tycho's remnant. 1604's flash with Kepler's. Each remnant is like a time capsule, connecting us to an epoch when people first looked skyward in wonder. We still remember these events, often naming the nebula after the observer, Tycho's supernova remnant, Kepler's, and so on. They remind us that the universe we see today is a living history book, full of stellar epics quietly recorded in light. Even when no distant explosion appears in our sky, astronomers know others are happening beyond our sight. In fact, each year, dozens of supernovae go off in other galaxies, unseen by ancient peoples, but caught by telescopes. Some are hidden by dust in our own Milky Way. Scientists sometimes detect faint X-rays or radio waves from a recent galactic supernova that happened before any telescope looked that way. We might call these ghostly echoes of lost explosions. But as soon as technology allows, we might connect them with new nebulae, adding to our cosmic ledger of stellar endings. The night sky continues to hold secrets of stars that died long before we were born. Yet through both modern technology and ancient record, we keep unveiling these cosmic stories. Every ghostly nebula and every faint historical note is a clue to the grand tale of how stars live and die. In the next chapter, we will follow this journey further, tracing the remnants as they fade back into the galactic tapestry. For now, let us rest under the same starlight that inspired our ancestors to look up in awe. The legacy of those exploding stars remains with us, a gentle reminder of eternity in the quiet of the night sky. When a massive star reaches the end of its life and explodes, it does something extraordinary. It becomes a cosmic forge. In those final moments, the dying star's core collapses under its own gravity, and unimaginably intense heat and pressure ignite a cascade of nuclear reactions. Protons and neutrons, once separate, are smashed together into brand new elements. In an instant of cosmic alchemy, the star's innards transform into a treasure chest of the heaviest elements in the universe. Iron, nickel, gold, platinum, uranium, even elements like gold and silver that humanity cherishes, are born in that fiery crucible. It is as if the star, in its death throes, becomes an alchemist, transmuting its own material into the richest substances of the cosmos. For ordinary stars like our Sun, fusion in their cores creates elements only up to iron. Iron is where regular fusion runs out of energy. But in a supernova's blast, something miraculous happens. A flood of free neutrons is unleashed from the collapsing core. These neutrons are captured in a flurry by the existing atoms, building them up into heavier and heavier nuclei in a process scientists call the R process, short for rapid neutron capture. In those few heartbeats of a star's death, tiny atoms grow into giants. Silver, platinum, gold, even the heaviest metals we know, they all form in that neutron-rich fire. The conditions are so extreme, so unlike anything on Earth, that the usual rules of nuclear chemistry are bent. In that brief cosmic flash, atoms beyond iron are forged out of nothing and then promptly flung into space. Imagine, for a moment, every piece of gold or silver you have ever held. Each wedding band, every shiny coin, all began as a handful of protons and neutrons deep inside a star. Each bit of metal is a direct product of those final stellar moments. Consider the devices in your hand. The copper wiring in a phone, the lithium in a battery. These too were formed in a star's core. The iron in the Earth's core, the uranium in nuclear reactors, the rare metals in our electronics, all trace their origin to a supernova. When you hold a gold ring or a silver coin, you are quite literally holding a piece of an ancient star. That bright sheen was once part of a distant supernova's glowing cloud. The treasures of our planet are written in the sky. For centuries, humans dreamed of alchemy, turning lead into gold. Ancient alchemists would have marveled at what happens in space. The stars themselves have achieved true transmutation on the grandest scale. In the silent emptiness between stars, there is no clamour or furnace. Yet at a star's end, elements are transmuted as if by magic. The universe contains its own alchemy, quietly and humbly distributing treasures among its heirs. Every gold medallion, every precious jewel, Every ton of iron mined from Earth's crust is a silent reminder that cosmic chemistry once forged it. The star's death is our birthright, a celestial gift of rare metals and minerals. The forging of these heavy elements happens almost in an instant. In a core collapse supernova, time is measured in heartbeats of the dying star. Within mere seconds of the core imploding, neutrons swarm through the furnace-like environment. Atoms capture these neutrons in rapid succession, ballooning into heavier nuclei in a process so quick scientists call it the R process. It literally bends the rules of nuclear physics for a moment, allowing elements from iron all the way up to uranium to be made on the fly. The elements form almost instantly and then are flung into space. It is cosmic creation at its most intense and fleeting. Even the neutrinos play a role in this cosmic alchemy. When the core collapses into a neutron star, it releases a flood of neutrinos, ghostly particles that flood outward. These neutrinos rarely interact with matter, but in these numbers they do have an effect. When a neutrino collides with a nucleus, it can turn a proton into a neutron, or vice versa, slightly altering the nuclear recipe. This neutrino wind gives one final tweak to the elements being formed, helping create certain isotopes of elements like copper and zinc that might otherwise be rare. In effect, the star's death throes include a last, subtle stirring of the material, ensuring a richer variety of elements is produced. Astronomers have even seen the results of this process in action. When we point telescopes at a supernova remnant, the expanding cloud left behind, we see unmistakable fingerprints of these new elements. In X-ray images of remnants, iron often glows brightly, showing where large amounts of it were blown out. Observatories have detected gamma rays from radioactive isotopes like nickel and titanium, confirming that those atoms were freshly forged in the explosion. Every new observation peels back another layer, confirming that supernovae really do enrich the cosmos with heavy elements. All of modern technology is, in a sense, borrowed from this cosmic heritage. The rare metals used in electronics, the magnets in motors, the catalysts in our machines. These are all products of ancient stellar furnaces. Every time we strip platinum, cobalt, or tantalum from the Earth, we are mining the legacy of long-dead stars. Every time we gaze at a sparkling metal, it's a wink from an ancestor star. Our smartphones, our batteries, the gold jewelry we admire, they all have origin stories reaching billions of years back in the hearts and deaths of stars. Yet even this glittering supply is but a subtle touch on a vast canvas. The heavy elements are rare. By mass, the universe is still overwhelmingly hydrogen and helium. A newborn star is almost all light elements. Only a tiny fraction, often a few percent by mass, is the heavy stuff. If the universe were a great work of art, the metals would be the fine brushstrokes adding colour. Supernovae sprinkle these colours gently, a dash of gold here, a flourish of iron there. It is this slight enrichment that makes the difference between a cosmos of dull gas and one alive with planets, oceans, and life. In a poetic twist, the death of one star truly becomes the beginning of many others. When that star explodes, its final moments rewrite the chemistry of space. The atoms it forged are swept into new clouds, where they can become part of planets, oceans, and living creatures. Thus, each star's end is the start of countless new stories across the universe. The star's last breath lays the foundation for everything that follows, turning death into promise. Yet the story does not end with precious metals. The star still has more to give. Beyond the firestorm, a vast cloud of gas and dust is hurled outwards, carrying every element the star created. As the blast wave expands into space, it cools and slows. In that cooling phase, particles collide and stick together. Complex molecules form, and tiny grains of dust condense from the enriched gas. Clouds of gas and dust, rich in metals and minerals, billow out into the galaxy. In this glowing nebula, the dying star's end is truly the dawn of new possibility, a nursery of raw material for worlds yet unborn. This cloud of stellar debris drifts through space, each microscopic grain a carrier of the star's legacy. Driven by the shockwave, every tiny speck of carbon, silicon, iron, and more floats outward. Though no larger than grains of smoke, these dust particles are the seeds of planets. They mingle with the vast hydrogen and helium clouds in the interstellar medium. When one of those clouds later collapses to form a new star, the dust is carried along. Within the swirling disk around that newborn star, dust grains stick together and grow into pebbles, then rocks, and eventually entire planets. Without this enriched dust from previous supernovae, rocky worlds like Earth could not exist. Even today, the fingerprints of ancient explosions are all around us. Some of the interstellar dust from long ago supernovae still drifts into our solar neighborhood. Tiny dust particles fall into Earth's atmosphere, and meteorites that survive their fiery fall can contain grains older than the solar system. Scientists have found in these pre-solar grains specific isotopic signatures that match stellar processes. Silicon carbide and microscopic diamonds in some meteorites, for example, were formed in other stars. By analyzing their composition, we can read the unique fingerprints of past supernovae and giant stars. Each of these dust grains is a tiny time capsule, carrying within it the story of its stellar birth. Look up at the Milky Way's spiral arms on a clear night. Some appear as bright nebulae glowing with hot gas. Others are dark lanes that blot out the stars behind them. These are made of dust, often enriched by old stars. In emission nebulae, young stars light up the gas and dust around them. In dark nebulae, thick dust blocks the background starlight. But in both cases, that dust owes its composition to countless earlier explosions. These dusty regions are nurseries of star formation, exactly the places where the ashes of old stars collect and condense into new ones. The very scenery of our galaxy is painted with the dust and gas from exploded stars. In fact, in our own cosmic backyard, that dust helped form our world. Many researchers believe that a supernova may even have triggered the sun's birth. Evidence comes from radioactive isotopes in meteorites, like aluminum-26 and iron-60, which decay too quickly to be left over from the Big Bang. Their presence suggests a nearby exploding star sprinkled fresh material into the cloud that became our solar system. In that scenario, a shockwave from a dying star crashed into the solar nebula, enriching it with heavy elements and perhaps nudging it to collapse. That means our sun and planets were literally born from a cloud of gas and dust, seasoned by ancient supernova. It's worth noting that cosmic dust is fragile. Later, supernova shockwaves or intense radiation can shatter these grains, vaporizing them back into gas. In this way, supernovae both create and destroy dust. Some older grains are crushed by new waves, while new grains condense from fresh explosions. Yet enough dust survives to keep the cycle going. Through countless stellar storms, the galaxy maintains a steady mist of dust, ever renewing itself. The grains of dust from exploded stars are literally the foundation of new worlds. Planets like Earth began as specks of this stardust swirling in the protoplanetary disk. Without that solid material, gravity alone could not assemble rocky planets. There would be nothing to coalesce. The dust provides the scaffolding for worlds. It's astonishing to think that the clay of future continents and the silica of future beaches were spread across space by long-dead stars. The elements and dust from supernovae do not all go into one place. They mix into the galaxy. Carried by the galactic winds and currents, this material spreads far and wide. Some of it drifts into one molecular cloud, some into another. Over time, the ashes of a single supernova can become ingredients in dozens or even hundreds of star systems. The heavy elements from that one star will scatter, seeding many new worlds. In that way, the universe is generous. The supernova's yield becomes communal property, a shared inheritance of the cosmos. Once out in the galaxy, these elements become part of the interstellar medium, ISM. Most of the ISM is still hydrogen and helium, but it's enriched by metals and dust from supernovae. Even a small percentage of heavy elements makes a big difference. For example, in a typical star-forming cloud, about 90% is hydrogen, 9% helium, and roughly 1% heavier elements. That 1% contains all the carbon, oxygen, iron, and everything else needed for planets and life. It sounds tiny, but without it, planets would be barren gas giants or rocky wastelands. Supernovae fill that critical 1% with life's building blocks. Inside these enriched clouds, the galaxy's next generation of stars will be born. Astronomers measure a star's metallicity, the fraction of elements heavier than helium, to see how many generations came before. The first stars, formed from pristine bigbang gas, had almost no metals at all. Each time a wave of new stars formed and died, the clouds became more enriched. Today, our sun is considered fairly metal-rich compared to those first stars, reflecting billions of years of recycling. By examining many stars, scientists can actually trace how the Milky Way grew richer with each generation. We find that stars near the galactic center, or in spiral arms, where many supernovae have gone off, tend to have higher metallicities, while older stars and those in quieter regions have fewer metals. In effect, the galaxy's structure and chemistry preserve a record of its history of star birth and death. This whole process, stars forging elements and then returning them to the gas, is nothing less than a cosmic recycling program. It's happening in every galaxy. Remnants of exploded stars mix with the interstellar gas like fertilizer, enriching a cosmic field. Over eons, generations of stars are born, live their lives, and die, each time adding to the mix. Like a great cycle of nature on a grand scale, each stellar generation sows the seeds of the next. With each supernova, the galaxy grows richer in heavy elements and dust, gradually building complexity. This ongoing alchemy is the universe's ultimate recycling machine, turning the death of old stars into the birth of new ones. Even seemingly empty clouds of hydrogen and helium are laced with these heavy elements. Astronomers often call everything heavier than helium a metal. In our galaxy, these metals include carbon, oxygen, silicon, iron, and many others. Countless generations of stars have peppered the Milky Way with these materials. When a new star forms from one of these mixed clouds, it inherits that enriched material. Over cosmic time, the galaxy steadily becomes more metal-rich. Young stars like our Sun can have rocky planets, and even the chemistry needed for life, because untold stellar ancestors have done the recycling for eons. The galaxy itself seems to behave like a living organism in these cycles. Star clusters fade and new ones ignite. Gas collapses into stars that later explode and send gas flowing again. Shock waves from supernovae can even trigger new star formation. When a blast hits a nearby cloud of gas, it can squeeze it just enough to ignite collapse. In that way, one star's death can literally sow the seeds for many new stars. Astronomers see this unfolding in nebulae across the sky. In stellar nurseries, they often find bubble-like structures and arcs, the scars of past supernovae sculpting future stellar cradles. Far from destroying the galaxy's material, each supernova lights a spark that helps make the next generation of stars and worlds. And as a result, the universe becomes gradually more hospitable and interesting. In its youth, it contained only hydrogen and helium, which by themselves could never make rocky planets or life as we know it. But each generation of stars added new elements to the mix. Now we live in a cosmos rich with diversity, where planets with iron cores, water oceans, and carbon-based life can form. It's as though the universe is slowly refining itself, like a master craftsman, step by step, building up the complexity that allows life and civilizations to emerge. The mountains, the oceans, even our bodies owe their existence to this quiet, steady enrichment. And among all the gifts of the stars, perhaps none matter more to us than the elements that make life possible. Carbon, oxygen, nitrogen, phosphorus, iron. These aren't just chemicals. They are the very ingredients of living cells. When we trace the origin of these elements, we find the fingerprints of dying stars. The carbon in our DNA, the oxygen we breathe, the iron in our blood. All were born in the hearts of ancient stars, or in their explosive ends. Massive stars generate much of the oxygen and silicon. Smaller stars create carbon through helium fusion. When these stars eventually expel their material, whether in gentle winds or in cataclysmic blasts, those life-essential elements spread into the galaxy. In this sense, life on Earth is quite literally built from star stuff. Without carbon, there would be no organic chemistry. Without oxygen, no water or breathable air. Without nitrogen and phosphorus, the molecules of life, like DNA and proteins, simply could not form. All of these crucial elements were delivered to the infant Earth by the galaxy. Through collisions and drifts, cosmic dust and meteorites enriched with star-made elements fell onto our planet. Every rain of dust, every flying meteorite carried materials forged in distant stars. Even today, supernovae continue to sprinkle the universe with raw ingredients that may one day become life elsewhere. We are connected to the stars, not just in spirit, but in substance. We are composed of atoms that have traveled across the cosmos. For example, our own world bears the marks of ancient explosions. When the sun and planets were forming, the nebula that became our solar system was already enriched by previous supernovae. We detect this heritage in the meteorites that rained down to Earth. Scientists have found exotic isotopes in these space rocks, elements that could only have been produced by a nearby exploding star. These clues suggest that one or more supernovae went off near our young solar system, sprinkling it with their elemental legacy. So when we feel the iron in our blood or the calcium in our bones, we are intimately touching the legacy of those dying stars. Every breath we take, every piece of the world we touch, is linked back to ancient stellar furnaces. In fact, every person is a continuation of this cosmic story. When we look at a human cell under a microscope, or gaze at our hand, we are seeing the legacy of supernovae. The water in our cells, the carbon chains in our bones, the metals in our blood, they are all heirlooms of the universe. Even the gold in our jewelry and the copper in our electronics are simply pieces of ancient stardust. When you hold something precious, remember, it may be a keepsake from a cosmic relative. Our place in the universe is just one link in the endless chain of inheritance. And that chain of inheritance truly has been going on since the very beginning. It stretches back to the first stars, which burned briefly in a now vanished era. Those original giants enriched the cosmos with the first heavy elements. The next generation of stars inherited that material and made more elements of their own. One star's layers of elements became the next star's raw material, and on it goes. The universe is like a vast family tree. Stars give birth to new stars, passing along their enriched DNA. Astronomers even name these generations. The oldest stars, with almost no metals, are called population 3. The next ones are population 2. Our Sun belongs to population 1. Each population is simply a record of how many generations have gone before. We, here on our small planet, are part of that great family. Every atom in our bodies has been passed down through an unbroken line. Our Sun, when it formed, was already littered with the ashes of dozens of earlier supernovae and evolved stars. That means countless stars contributed material that became our planets, our oceans, our very cells. In a way, each person contains atoms that were once part of stars that lit up the early universe. We truly are children of the cosmos, cosmic grandchildren of those ancient supernovae. And the story does not end with our generation. Even now, the chain continues. When our Sun eventually exhausts its fuel, in about 5 billion years, it will cast off its outer layers, spreading carbon and oxygen into space. Those elements will join the galactic medium, ready to be swept into new clouds and build future stars and planets. Over eons, the atoms in our bodies and our world will drift away, perhaps incorporated into alien worlds far in the future. In this way, the elements of life pass like a baton from one generation to the next, an eternal relay of matter. It's as if every star hands down a family heirloom to its descendants. Each generation adds a few more accessories to the cosmic wardrobe. Over cosmic time, the galaxy's metal content has slowly increased. Astronomers have measured this metallicity and found that young stars today are richer in heavy elements than stars that formed billions of years ago. The Milky Way has been steadily building its inventory of elements, from nearly none shortly after the Big Bang to the diverse palette we see now. In this grand process, our Sun and its planets are an inheritance from all that history. One might even say the universe is the ultimate recycler, never letting any material go to waste. The ashes of each supernova become the compost of the next cosmic garden. Every atom of metal in the galaxy gets a second, third, or fourth chance as it cycles through new stars and planets. The galaxy itself feels alive in this way, continuously renewing its stock of star-making ingredients. In the stillness between the stars, this quiet recycling never stops. When we gaze up at the night sky, we are looking at members of our cosmic family. The glitter of stars above is a reminder that those blazing suns have either lived or will live lives not so different from our own suns. They glow with the gifts of their ancestors, and someday they too will explode and pass their gifts onward. The cosmos is an intricate fabric of inheritance, connecting one generation of stars to the next, linking us to the ancient past and to the unfolding future. The story of the universe is an unbroken tapestry of star stuff, and we are woven right into its design, living proof that out of star death comes life, and from endings arise new beginnings. When a massive star exhausts its fuel and explodes in a brilliant supernova, the story doesn't end with that burst of light. In the hushed aftermath, when the expanding clouds of gas drift away and the sky grows dark again, what remains of the star is something extraordinary. It's a small, dense core, the heart of the star, but transformed into an unimaginably compact object called a neutron star. Imagine compressing a mass greater than our sun into a sphere only about the size of a city. In other words, a teaspoonful of this neutron star material would weigh about 1 billion tons on Earth. Here in this tiny, city-sized ball, atoms have been crushed until the electrons and protons have fused, leaving a sea of neutrons packed together. The result is a star of almost inscrutable density, a cosmic coffin containing the atoms of the old star in a new form. This remnant, this stellar corpse, is extraordinarily strange. Its gravity is crushing, so intense that any matter or light falling on it will be pulled in with immense force. The surface gravity is billions of times stronger than Earth's, meaning that if you could stand on a neutron star's surface, and you cannot, a person there would weigh more than Mount Everest. But the neutron star doesn't shine in visible light. Instead, it may glow faintly in X-rays, or emit particle winds, slowly cooling over thousands of years. In the darkness of space, a lone neutron star can be almost invisible, save for a faint glow or subtle presence that only special instruments can detect. It is, quite literally, a ghost wandering the cosmos, the final hushed trace of a star's life. But even in their silence, many neutron stars carry one more secret. They often spin. During the collapse that formed them, the law of conservation of angular momentum takes effect. A star that was once spinning even a little suddenly shrinks to a fraction of its original size. Like a figure skater pulling in her arms, the remnant spins up dramatically. Some neutron stars rotate with astonishing rapidity, spinning dozens or even hundreds of times per second. The fastest known spinning neutron star, a millisecond pulsar, whirls around almost 1,000 times in a single second. To imagine this, picture a city-sized sphere rotating so fast that its surface moves at thousands of kilometers per second. If there were any mountains on its surface, they would melt or be flung off by the motion. But thanks to the star's gravity and solid crust, even tiny mountains might endure. This rapid spin gives neutron stars another peculiar character. Many carry intense magnetic fields, far stronger than anything we encounter on Earth. As the star collapsed, its magnetic field lines got concentrated, becoming trillions of times more powerful. Around a neutron star, the space is threaded with these ferocious magnetic fields, forming a magnetosphere that can fling charged particles at incredible speed. If the magnetic axis of the neutron star is tilted with respect to its spin axis, these charged particles can spiral out along the poles, shooting beams of radiation into space. From far off, these beams may not be easily visible, but they carry energy in forms like X-rays and radio waves. In some neutron stars, this beam mechanism manifests in an extraordinary way. They emit pulses of light or radio waves with clockwork regularity. But more on that in a moment. First, Picture the neutron star itself. Its surface is only a few kilometers thick, but below it lies something even stranger. Physicists believe the interior of a neutron star is a superfluid of neutrons, possibly with a core of exotic particles or even strange quark matter. Deep within, gravity squeezes matter to such extremes that the usual rules of chemistry and atomic structure break down. The result is a kind of nuclear pasta, layers and structures unlike anything on Earth, held together by forces that scientists are still striving to fully understand. Despite their exotic interiors, neutron stars often give themselves away. Some are young and still glowing from the heat of formation. If a neutron star is less than a few 100,000 years old, it may shine in X-rays, slowly cooling like a dying ember. Astronomers have spotted such cooling neutron stars, faintly visible in X-rays against the darkness. Others reveal themselves by interacting with their environment. For example, the famous Crab Nebula hides within it a rapidly spinning neutron star, the Crab pulsar, which emits beams of radiation and powers the glowing nebula around it. In these cases, the neutron star is not truly silent. It lights up its surroundings in subtle but telling ways. Some neutron stars, however, remain almost completely invisible until they do something special. For instance, if a neutron star drifts through space and encounters gas or dust, it can sweep it up. This material heats as it falls and can make the neutron star briefly glow. Or, if a neutron star still has any companions, it might pull matter off a neighboring star, forming an accretion disk and bright emission. In solitude, though, an old neutron star could drift for millions of years unnoticed, its presence betrayed only by tiny wobbles in the positions of nearby stars due to its gravity. These dense corpses spin in the dark, truly silent survivors of cosmic death. Among these cosmic ghosts, there are special cases that seem to awaken and speak to us. Some neutron stars turn their silent spin into a rhythmic message, pulses. These pulsars are the subject of our next exploration. Imagine a scenario. A neutron star's magnetic poles align at an angle to its rotation, and jets of radiation pour from those poles like cosmic searchlights. As the star spins, those beams sweep around like the rotating beam of a lighthouse. If one of those beams sweeps past Earth's line of sight, we see a flash of radio or X-ray light once every rotation. This is the essence of a pulsar, a spinning neutron star whose lighthouse-like beams create a beat of radiation in space. The effect is subtle from a distance. A pulsar might emit radio waves, gamma rays, or X-rays, but we only detect them as pulses. It is as if an invisible drum in the universe beats at an interval of seconds or milliseconds, letting us know that a neutron star is still there. Some pulsars pulse every few seconds, others pulse hundreds of times each second. Their rhythms are astonishingly regular. In fact, they are so reliable that if you knew a pulsar's pattern, you could set your watch to it. The discovery of the first pulsars in 1967 by astronomers Jocelyn Bell Burnell and Anthony Hewish was a watershed moment. They noticed a repeating radio signal in their telescope data, a sharp, evenly spaced series of ticks coming from a fixed point in the sky. At first, they named it LGM1, Little Green Men, as a joke, wondering if it might even be a signal from intelligent beings. But careful observation soon revealed that the signal was coming from a rapidly spinning neutron star, and thousands of such pulsars have been found since then. Each is like a cosmic metronome placed in the galaxy, ticking away at its own steady rate. These celestial clocks have profound uses. Because a pulsar's timing is so precise, we can use them to study the galaxy. By measuring tiny variations in the arrival times of pulses, astronomers can infer if the pulsar has a companion tugging on it, or if gravitational waves from distant events stretch space, or even use a network of millisecond pulsars to search for the cosmic background of gravitational waves. One of the most famous examples is the double pulsar system, where two neutron stars orbit each other, both acting as pulsars. Watching their pulses allowed scientists to test Einstein's theory of general relativity to high precision, confirming that gravity behaves exactly as predicted in one of the most intense laboratories imaginable. Not all pulsars are born equal. Some are isolated, but many are in binary systems. In fact, one class of pulsars, called millisecond pulsars, are thought to have been recycled. In this scenario, an old neutron star slows down with age, but if it has a companion star overflowing with gas, the gas can be captured by the neutron star and spin it up like a satellite receiving momentum. The result is a neutron star spinning hundreds of times per second, a pulsar with a millisecond period. These ultra-fast pulsars are even more accurate clocks and tell us stories of accretion and mass transfer that happened long ago. When you listen to a pulsar, it is like hearing the steady heartbeat of a corpse that's still very much alive in a way. A neutron star that seems silent can announce its presence with each pulse. From Earth, we may only catch a faint ping or flash once per rotation, but each one is a powerful message from an object tens of thousands of light years away. It speaks of the physics of dense matter, of magnetic dynamos, and of the cosmic geography of our galaxy. In many ways, pulsars are not just survivors, they are informants, giving us clues about the universe that we could not get otherwise. As we revel in the rhythm of pulsars, another phenomenon reminds us that not all starlight comes in pulses or glows. Some stars, even after exploding, vanish in silence when the progenitor star is heavy enough. Sometimes the collapse is complete and nothing is left but a black hole. Unlike neutron stars, black holes give away nothing in light. A black hole is born if the stellar core is too massive. The collapse continues beyond the neutron star stage, and gravitational forces squeeze the core into a point of infinite density, called a singularity, surrounded by an event horizon. The event horizon is the boundary of the black hole, a surface in spacetime beyond which nothing can return. Not light, not particles, nothing. It is the ultimate cosmic trap. This event horizon can be thought of as the point of no return. If any object gets within this radius, the Schwarzschild radius, it cannot escape. For a black hole with 10 times the mass of the Sun, this radius is about 30 kilometers. Imagine compressing 10 suns into a sphere no larger than a small city, and then stretching an invisible sphere around it from which no signal returns. Inside, space-time is curved so severely that even light is compelled to spiral inward. Outside, gravity behaves normally, and distant observers can study the region by watching how light and objects behave in the black hole's gravity. Even though a black hole itself is black, we can still infer its presence in clever ways. If a black hole has a companion star or leftover gas, that material can form an accretion disk around it. As gas spirals in, it heats up and glows brightly in X-rays, betraying the black hole's location. In our galaxy and others, astronomers have found many such X-ray binaries where the unseen partner is a black hole. Additionally, if a star happens to pass too close to a black hole, it can be torn apart in a tidal disruption event, producing a flare that we can observe. These clues are how we know black holes live among us. Black holes are also thought to be the engines of some of the universe's most energetic phenomena. For example, jets of high-energy particles blasting out from galactic centers are believed to be powered by supermassive black holes, and even stellar mass black holes can produce jets as they accrete matter. But let us not stray too far. Our focus here is on the black holes born from the fiery death of individual stars. Another spectacular way black holes have announced themselves to humanity is through gravitational waves. In 2015, the LIGO detectors heard the faint tremor of spacetime as two stellar mass black holes spiraled together and merged. This cosmic collision happened over 1 billion light-years away, but the ripples reached Earth and were measured. The death dance of these massive bodies was recorded as the universe's newest messenger. Such an event taught us not only that black holes form binaries, but also that their mergers shape space-time itself. In the cold vacuum left by a star's explosion, a black hole becomes the epitome of silence. It doesn't shine, it doesn't pulse, it simply waits. Yet its gravitational presence can continue to shape its surroundings. It can lasso gas, tug on stars, and influence the evolution of galaxies. It is a fittingly mysterious end to the story of the heaviest stars, from blazing light to utter darkness. Now, we have encountered 3 kinds of survivors: the silent but spinning neutron star, the pulsating beacon, and the invisible black hole. But in the universe's grand theatre, there are still more characters to meet. Especially interesting are what happens when these survivors are not alone. Many stars spend their lives in pairs, locked in a gravitational dance with a companion. When one star in a binary explodes, it can change the life of the other forever. Imagine 2 stars orbiting each other. If one goes supernova and leaves behind a neutron star or black hole, the newly orphaned companion may be hurled into space by the explosion's kick, becoming a runaway star racing through the galaxy. Or, sometimes, the system remains bound. In that case, the neutron star or black hole finds itself in a new binary system. Now, if the companion is still alive, it might transfer matter onto the compact remnant. This process can strip the outer layers off the companion, and the material will swirl around the neutron star or black hole, forming a bright accretion disk. Such systems are known as X-ray binaries, and they can shine extraordinarily bright in X-rays for as long as the feeding continues. This is another pathway through which a once dead star exerts influence long after its explosion. In some double star systems, the companion will itself eventually reach the end of its life. If it too is massive enough, it can go supernova, leaving a second neutron star or black hole. The pair then becomes an exotic binary, for example, a binary neutron star system or a neutron star paired with a black hole. When 2 neutron stars orbit closely, they emit gravitational waves and gradually spiral together over millions of years until they finally merge. The recent observation of gravitational waves from such a merger, accompanied by a luminous kilonova explosion, confirmed that heavy elements like gold and platinum are forged in these cosmic furnaces. 2 neutron stars coalescing is like a grand finale on top of a long drama, a final liberation of energy that ripples across the universe. But even before any merger, these systems have dramatic lives. A neutron star in a binary can become a pulsar and slowly eat its companion star. As it gains mass and spin from the infalling material, it can light up the sky or speed up its own rotation. Indeed, many of the fastest millisecond pulsars we observe are in binary systems, where mass transfer has spun them up. Alternatively, if the binary is tight and the orientation is right, we might see eclipses of pulsar signals as the companion passes in front of the neutron star. Astronomers have even detected triple star systems with a pulsar, where a neutron star orbits closely with two other stars. The dynamics of such systems make them laboratories for testing gravity and the end stages of stellar evolution. Binary systems can also affect star formation itself. Sometimes a supernova explosion can compress nearby gas clouds or trigger shock waves that initiate the birth of new stars. In this sense, the death of one star could be the spark that ignites another. Conversely, if the companions are small, the supernova blast might simply tear the pair apart, sending them each on lonely voyages. The diversity of outcomes shows that binary systems can lead to a rich variety of strange survivors and exotic phenomena. We see evidence of binary effects all over the sky. The bright X-ray source, Cygnus X1, for example, is a system where a black hole feeds on a massive stellar companion. The famous Hulse-Taylor binary pulsar, two neutron stars orbiting each other, gave us the first indirect evidence of gravitational waves. The merger event, GW170817, involved a binary neutron star and produced a radiant afterglow visible across the electromagnetic spectrum. Each of these is a chapter in the story of explosions reshaping stellar companions. In every case, the explosion of one star alters the course of another. A companion star may suddenly find itself spun up, stripped bare of its outer layers, or accelerated to high speed, or it may inherit new elements deposited by the supernova. The interplay of binary stars gives rise to phenomena as diverse as millisecond pulsars, X-ray binaries, gamma-ray bursts, and sources of gravitational waves. We call these patterns the binary fates of stars, how one star's end is bound to another's destiny. Even more exotic than double stars are some rare breeds of stellar remnants whose conditions are so extreme they break all our earthly intuitions. Among the strangest are the magnetars. A magnetar begins life like a neutron star, but under the right conditions, especially if the star had a very fast spin at birth, its magnetic field gets amplified to mind-boggling strength. A typical magnetar's magnetic field can be around 10 to the 15th Gauss. For comparison, the strongest magnets we make in labs on Earth are maybe 10 to the 5th Gauss. So a magnetar is 1 trillion times stronger than those. What does such a magnetic monster do? Inside a magnetar, the field is so intense that it twists and strains the matter and the very vacuum around it. Occasionally, this stress becomes too much. The crust of the magnetar, which is solid and under immense pressure, can crack or shift in a starquake. When that happens, the magnetic field can suddenly realign, releasing an enormous amount of energy in a flash. The result is a burst of high-energy radiation, X-rays or gamma rays, that blasts into space. These magnetar flares are unimaginably powerful given the tiny size of the star. In 2004, astronomers detected one of the most dramatic magnetar flares ever observed. A magnetar known as SGR 1806-20, over 50,000 light-years away, erupted and produced a flash of gamma rays so intense that it momentarily ionized Earth's upper atmosphere. Even though it was halfway across our galaxy, it became the brightest extrasolar event recorded at the time. For a fraction of a second, this distant object was the brightest thing in our sky. It was as if a city-sized object had unleashed the power of 1 billion atomic bombs in one quick pulse. Magnetars show us that even the survivors of supernovae can sometimes explode again in different ways. These stars have been called the universe's most magnetic monsters. Some of them, called anomalous X-ray pulsars or soft gamma repeaters, are seen as pulsing X-ray sources or repeating gamma-ray bursts. Each flare changes our understanding of physics because the conditions on a magnetar are beyond what we can replicate on Earth. Studying these outbursts is like peering into an alien laboratory where magnetic forces rule supreme. There's even a tantalizing connection between magnetars and some of the most mysterious signals we receive from space. Fast radio bursts, FRBS, are fleeting, millisecond-long pulses of radio waves from distant galaxies, and their origin has puzzled astronomers. Recently, evidence suggests that at least some FRBS may come from magnetars. If so, it means a magnetar's outbursts could be sending not just X-rays, but also radio flashes across the universe. Every time a magnetar flares, it imprints a piece of its story on the cosmos. In the grand tapestry of the universe, we have now met many strange survivors of stellar death, the neutron stars spinning silently in the darkness, city-sized and nearly invisible, the pulsars that broadcast their presence in rhythmic signals, like cosmic lighthouses guiding our telescopes, the black holes that collapse beyond light, dragging everything that dares to approach across the event horizon and into silence, the binary systems, where one star's death molds the fate of another, creating new spectacles of light or altered orbits, and the magnetars, magnetic leviathans that occasionally remind us of their power with bursts of energy that shine across the galaxy. Each of these survivors carries a piece of the supernova's legacy. They forge heavy elements like gold and uranium. They seed shockwaves that birth new stars. They curve space and whisper secrets of physics. They may be the quiet husks of exploded stars, or they may be active beacons and engines shaping galaxies. And in every case, their existence is a testament to nature's ability to turn an ending into a new beginning. There are even more wonders still hidden in these tales. For example, some runaway neutron stars race through space at incredible speeds, as though thrown by their birth explosion, zipping past star clusters. Others may have planets of their own, tiny rocky worlds orbiting around a dead star. And the space around these objects can create nebulae and shock fronts that glow for millennia. The universe is full of these connections between life and death on a cosmic scale. The strange survivors of supernovae are not the conclusion of the story, but rather a continuation, a bridge between the explosive death of old stars and the quiet birth of new ones. They remind us that even in silence, there can be a message. Even in darkness, there can be a light. Our exploration of supernova legacies has revealed just how rich that story can be. And yet it is far from over. As we drift onward in our cosmic journey, we carry with us the echoes of those stellar explosions and their aftermath. The sky is filled with subtle clues and glowing remnants, each pointing to the fact that death and rebirth are woven into the fabric of the universe. Our voyage has taken us through light and through shadow, through lighthouses and through black holes. And still, the horizon of discovery stretches further. The strange survivors we have met here are a chapter in the grand epic of the cosmos, and the next chapter awaits beyond the edge of the dark. The conversation continues with a gentle acknowledgement that the fires we have explored still burn across the cosmos. Massive stars are not isolated actors. They influence their surroundings profoundly. When such a star exhausts its fuel and collapses, the resulting explosion sends shockwaves coursing through the interstellar medium. These shockwaves carry heavy elements and energy, stirring clouds of gas and dust, and sometimes compressing them, setting the stage for new stars to form. Within a galaxy, the collective effect of many such explosions shapes its evolution. Each blast injects kinetic energy into the surrounding gas, disrupting quiescent regions and triggering bursts of star formation. The interplay between turbulence and gravity becomes a cosmic dance. While shock waves compress the clouds, gravity squeezes them further until gravity wins and a new star ignites. Over millions of years, this cycle of death and rebirth governs the rhythm of galactic life. As we imagine these shock waves rippling outward, think of how one star's end becomes another star's beginning. The compressed material succumbs to gravitational collapse, and protostars ignite in the shadows of their predecessor. This triggered star formation is not an isolated event, but a cascade. A single supernova can set off a chain reaction that births a cluster of new suns. The resulting region glows with fresh light, illuminated by the energy of the explosion that preceded it. Supernovae are also engines of chemical enrichment. The lighter elements forged in the cores of stars and the heavier elements produced in the explosion are flung into space. Oxygen, silicon, and iron are added to the galactic medium, where they mingle with hydrogen and helium. Over generations, this process raises the metallicity of galaxies, and future stars incorporate this enriched material, giving rise to planetary systems. The energy released by a supernova can blow bubbles in the interstellar medium. These bubbles, or superbubbles, expand and sometimes merge, carving cavities in the galactic disk. When two bubbles intersect, the compressed walls can collapse, forming dense regions ripe for star birth. Thus, the spatial pattern of star formation is sculpted by past explosions, and the distribution of stars across a galaxy carries the imprint of ancient cataclysms. Supernova remnants also accelerate particles to near light speeds, creating cosmic rays. These high-energy particles propagate through the galaxy, interacting with magnetic fields and gas. Cosmic rays heat and ionize the interstellar medium, influencing its chemistry and temperature. They contribute to the pressure balance of the galactic disk, altering how gas clouds collapse and when stars can form. Galactic fireworks are both creators and regulators. When explosions occur in dense star-forming regions, the shock waves can disrupt gas clouds, dispersing them before they collapse. In this way, supernovae regulate the rate of star formation, preventing a galaxy from consuming its fuel too quickly. Too many explosions blow away the gas. Too few allow runaway collapse, so the galaxy finds a dynamic balance between creation and destruction. Within the Milky Way, evidence points to supernova remnants as key accelerators of cosmic rays. Observations by space telescopes reveal signatures consistent with protons gaining energy from shockwaves. As these particles traverse the galaxy, they carry information about their origin. When they collide with interstellar gas, gamma rays are produced, lighting up clouds in telling patterns. Cosmic rays are subtle sculptors of the medium. Though invisible to our eyes, they influence the ionization state of gas, affecting the formation of molecules like carbon monoxide and water. Their presence can slow down the collapse of clouds, or, conversely, aid in stripping electrons from atoms, making them more reactive. In this way, the aftermath of a supernova reaches far beyond the immediate blast. touching the chemical and thermal properties of vast regions. Galaxies do not evolve in isolation. They interact with one another, and the combined feedback from supernovae can determine how gas is retained or lost. In dwarf galaxies, a flurry of explosions can eject gas entirely, leaving behind a faint skeleton of stars. In massive galaxies, the deeper gravitational well can hold onto the gas, but the outflows shape its distribution, creating halos of enriched material that later rain back down to fuel further star formation. Observations of nearby galaxies show arcs and shells of gas shaped by successive explosions. In starburst galaxies, where star formation rates are high, the cumulative effect is dramatic. Hot winds blow out of the galactic plane, carrying metals and energy into the halo and beyond. These winds interact with the intergalactic medium, contributing to the enrichment of the cosmic web and influencing the evolution of surrounding structures. The heavy elements propelled by supernovae are essential for the formation of planets and life. Without them, there would be no rocky worlds, no water, and no complex chemistry. Each galaxy's history of explosions determines its inventory of elements. As the metallicity of the interstellar medium increases, the types of stars that form also change, favoring smaller, longer-lived stars like the Sun in enriched environments. The Milky Way reveals a metallicity gradient that tells a story of time and place. The central bulge is rich in metals, reflecting an intense early period of star formation and supernova activity. The outer disk is more pristine, showing fewer heavy elements, indicating slower enrichment. Spiral arms, with their mixture of young and old stars, display a patchwork of ages and compositions, each a clue to past explosions and the movement of gas. When we map the metallicity of stars across the galaxy, we trace the history of explosions. Younger stars near the Sun incorporate material from countless earlier supernovae. Their composition reveals the contributions of core collapse and type Ia events, each leaving a unique imprint. By examining stellar spectra, astronomers piece together the cosmic genealogy of our neighborhood. Beyond the Milky Way, surveys of distant galaxies show how feedback shapes cosmic evolution. In the early universe, galaxies were small and irregular, experiencing vigorous bursts of star formation. Supernova feedback expelled gas, slowing growth and regulating the pace of star formation. Over time, galaxies merged and matured, and the cosmic star formation rate peaked about 10 billion years ago before declining, partly due to the regulating influence of these explosions. There is compelling evidence that a supernova shockwave triggered the formation of our own solar system. Radioactive isotopes found in meteorites suggest that a nearby explosion enriched the protosolar nebula with short-lived nuclides. The shockwave may have compressed the cloud, prompting it to collapse and form the Sun and planets. If true, our birth was catalyzed by the death of a massive star, a direct link between supernovae and the existence of Earth. The cosmic environment is influenced not only by the physical blast, but also by radiation. Ultraviolet and X-ray photons from supernovae and their remnants ionize gas across light years. This radiation affects the chemistry of surrounding clouds, breaking apart molecules and creating ions that act as catalysts for new reactions. Such effects are subtle yet pervasive, ensuring that the aftermath of a supernova resonates across many forms of energy. Within star clusters, the death of massive stars can dynamically reshape the cluster. The sudden loss of mass changes the gravitational potential, potentially ejecting other stars or altering their orbits. In young clusters, This can unbind the group entirely, dispersing its members throughout the galactic disk. The distribution of stars we see today carries evidence of such disruptions, revealing how individual explosions can scatter communities of stars. Galactic evolution is therefore a story of feedback loops. Stars form from gas, evolve, and explode. The explosions heat and stir the gas, controlling the next generation of stars. This self-regulation acts as a natural thermostat for galaxies. Too much star formation leads to more explosions and stronger winds, which push gas out and reduce star formation. Too little star formation leaves gas to accumulate until gravitational collapse resumes, and the cycle oscillates. In addition to common elements, supernovae produce exotic isotopes through processes such as the R process. These isotopes include gold, platinum, and uranium. When these elements are spread across the galaxy, they become part of planets and asteroids. The presence of such rare elements in Earth's crust hints at ancient supernova contributions, reminding us that luxury and technology alike owe their existence to these cataclysms. Astrophysicists act as cosmic archaeologists, seeking out the remnants of past explosions to reconstruct events. Supernova remnants reveal their age through the expansion of their shockwaves and their composition through spectral lines. Observations across radio, optical, X-ray, and gamma-ray bands provide complementary information. By studying these remnants, scientists infer the energy released, the mass of the progenitor star, and the geometry of the explosion, further elucidating the role of supernova in galactic ecosystems. Recent observations confirm that supernova remnants accelerate protons to high energies. The Fermi Gamma Ray Space Telescope detected gamma rays from collisions between accelerated protons and gas clouds. This provides direct evidence that these remnants are sources of cosmic rays. Such discoveries refine models of how energy is distributed in galaxies and support theories that supernovae are the primary accelerators of galactic cosmic rays. The interplay of supernova feedback and galactic dynamics shapes morphological features. The thickness of a galactic disk can be influenced by the vertical support provided by hot gas and cosmic rays. Outflows from star-forming regions drive gas perpendicular to the disk, puffing it up. Over cosmic time, repeated outbursts can create thick disks or halos of diffuse gas, and the Milky Way's own thick disk may owe part of its structure to ancient feedback. Galaxies also experience cycles of quenching and rejuvenation. When gas is expelled or heated by supernovae and active galactic nuclei, star formation slows or halts. Eventually, gas can cool or be reaccreted, leading to new waves of star formation. In some galaxies, this leads to episodic bursts of activity separated by quiet periods. Understanding these cycles helps astronomers explain the diversity of galaxy types and the evolution of the cosmic star formation history. The heavy elements seeded by supernovae also serve as tracers for astrophysical processes. Iron lines in the spectra of distant galaxies indicate the presence of Type 1a supernovae, which are used as standard candles to measure cosmic expansion. Oxygen and neon lines reveal the influence of core collapse supernovae. By analyzing these lines across large surveys, astronomers map the rate and distribution of supernovae over cosmic time, shedding light on both stellar evolution and cosmology. Magnetic fields thread the interstellar medium like invisible scaffolding. When a supernova explodes, its shockwave can amplify these fields, twisting and stretching them as it propagates. The interplay between turbulence, radiation, and magnetism influences how gas flows around the remnant. In some regions, the amplified fields confine cosmic rays. In others, they channel energy outwards. Such complexity underscores that galaxies are shaped by forces both visible and hidden. Different kinds of supernovae leave different chemical fingerprints. Core collapse events come from massive stars and enrich their surroundings with oxygen, magnesium, and the lighter alpha elements. Thermonuclear, or Type Ia explosions, originate in binary systems where a white dwarf accretes material until carbon fusion runs away, producing iron peak elements like nickel and iron. The relative rates of these events determine the mix of elements in future stars. In the earliest galaxies, the first stars were massive and short-lived. Their explosions seeded the pristine universe with the first heavy elements, enabling subsequent generations of stars to form at lower masses. As time passed, the feedback from supernovae moderated star formation, preventing young galaxies from collapsing into overly dense systems. This delicate balance allowed structures to grow gradually, laying foundations for the cosmic architecture we observe today. Galactic centers host supermassive black holes that can also influence star formation. Outflows driven by active galactic nuclei interact with supernova-driven winds, and together they regulate the gas supply. Sometimes these feedback processes cooperate, sweeping gas into dense shells where stars form. At other times they compete, clearing gas and quenching star formation. Understanding this interplay remains a frontier of galaxy evolution. Not all star formation triggered by supernovae proceeds in the same way. In some regions, a single explosion compresses a small cloud and forms a handful of stars. In other regions, multiple overlapping shock fronts create large-scale compression, igniting entire clusters. The timing between explosions, the density of the medium, and the orientation of magnetic fields all influence the outcome. Thus, the same physical event can produce a mosaic of responses. Galaxies accrete gas from cosmic filaments that thread the cosmic web. This inflow fuels star formation, while supernova-driven outflows expel gas, creating a dynamic exchange between galaxy and environment. The balance between inflow and outflow determines how quickly a galaxy grows. Feedback from exploding stars plays a central role in maintaining this equilibrium, ensuring that galaxies neither suffocate nor starve. Galaxy mergers can trigger intense starbursts by funneling gas into central regions. The resulting burst of star formation leads to a flurry of supernovae, which in turn drive powerful winds. These winds can blow out much of the newly formed gas, self-terminating the burst. In this way, gravitational dynamics and stellar feedback work together to shape the star formation history of merging systems. Over time, repeated supernova-driven winds can transform a galaxy's morphology. Gas removal may convert a spiral into a more spheroidal system, a process known as morphological quenching. Without gas, star formation dwindles, and the galaxy ages passively. The outlines of elliptical galaxies may thus bear the imprint of ancient supernova feedback, etched into their smooth profiles. Cosmic rays accelerated by supernova remnants also amplify magnetic fields on galactic scales. As these particles stream through the medium, they excite instabilities that tangle and strengthen magnetic field lines. Stronger fields, in turn, influence the propagation of future cosmic rays, creating a feedback loop. This subtle interplay helps explain why galaxies exhibit coherent magnetic structures despite the chaotic nature of their gas dynamics. Supernovae are not silent. They emit neutrinos and, if asymmetries exist, gravitational waves. During core collapse, a flood of neutrinos carries away energy, announcing the event long before light emerges. In rare cases, the violent stirring of spacetime can generate ripples that propagate across the universe. Detecting such signals complements electromagnetic observations and promises to reveal hidden facets of stellar death. Galaxies are part of a baryon cycle that exchanges matter with their surroundings. Gas accreted from the intergalactic medium flows into a galaxy, where it cools and forms stars. Supernovae and stellar winds then drive some of that material back out, heating and enriching the surrounding medium. This continual circulation blurs the boundaries between galaxy and environment, making each system both a recipient and a donor in the cosmic economy of matter. The intergalactic medium itself is enriched by supernovae. Metals observed in the space between galaxies trace back to winds driven by star formation. Over billions of years, these outflows have seeded the cosmic web with heavier elements, subtly changing the physics of gas far from any star. Even the vast voids are not untouched by stellar death. They contain whispers of explosions that occurred in ancient galaxies. Supernovae contribute to the diffuse glow of the universe. The cosmic infrared background includes light from countless dust-enshrouded supernovae and their remnants. As dust absorbs ultraviolet and optical photons from explosions, it re-emits the energy in infrared wavelengths. Observations of this background provide clues about the history of star formation and the frequency of supernovae across cosmic time. Dust grains are both created and destroyed by supernovae. In the dense regions behind shockwaves, molecules condense into solid particles, forming silicates and carbonaceous grains. However, subsequent shocks can shatter or erode this dust, returning it to gas. The balance between dust formation and destruction affects the opacity of galaxies, the cooling of gas, and the formation of planets. Supernovae thus play a dual role in the life cycle of dust. The future of supernova research is bright. Upcoming observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will monitor the sky with unprecedented sensitivity and cadence. They will detect thousands of supernovae, including rare types, allowing us to test theoretical models and refine distance measurements. Space-based neutrino and gravitational wave detectors may soon catch signals from nearby explosions, completing the multi-messenger picture. Star clusters play a special role in the interplay between supernovae and galactic evolution. In clusters rich with massive stars, multiple supernovae can occur within a few million years. Their combined winds and shockwaves carve out superbubbles that merge and distort the surrounding medium. The pattern of triggered star formation around these clusters creates arcs and rings of new stars, marking the footprints of their explosive progenitors. Chemical signatures allow astronomers to trace supernova contributions across cosmic time. Ratios of elements like magnesium to iron or europium to oxygen vary depending on the types of supernovae that enriched a region. By measuring these ratios in stars and gas clouds at different distances, scientists reconstruct the history of enrichment. Such studies reveal when different types of supernovae dominated and how their yields shaped subsequent generations. Thus, the fire of exploding stars is not merely destructive. It is generative and informative. It shapes the architecture of galaxies, modulates their star formation, enriches their chemistry, and provides tools for measuring the universe. From the smallest dwarf galaxy to the largest spiral, supernovae leave indelible marks. In the next reflections, we move from these broad scales to the intimate realm of our own bodies, carrying the legacy of many such explosions within us. Each breath we take and every beat of our hearts connects us to the cosmos. The oxygen that courses through our blood was forged in the core of a star and released when that star shed its outer layers. The carbon that forms the backbone of organic molecules was created by helium fusion in another star. Even the nitrogen in our DNA and the calcium in our bones trace their origins to these cosmic furnaces. After the Big Bang, the universe consisted almost entirely of hydrogen and helium, with traces of lithium. Heavier elements had to be created inside stars through nuclear fusion. In intermediate mass stars, fusion produces elements up to iron, which can be dispersed by stellar winds. Only when massive stars explode as supernovae are elements heavier than iron formed and ejected, including the iron in our blood and the calcium in our skeletons. Supernovae scatter both the elements made during a star's life and those synthesized in the explosion itself. Their shock waves propel material into space, mixing it with interstellar gas. Over millions of years, this enriched material forms new stars and planets. Each of us is thus built from atoms that have been inside multiple stars across successive generations before coalescing into living cells. Consider the calcium in our bones. This element was forged by nuclear reactions in the cores of stars that reached temperatures and densities high enough to fuse smaller nuclei. When such stars ended their lives, the calcium was expelled into space. Eventually, it became part of the dust cloud that formed our planet, and that calcium now supports our skeletons, linking us physically to ancient stars. Likewise, the iron in our blood was born in the core of a massive star and released during its final explosion. Without supernovae, there would be no iron to bind oxygen for transport in our bodies. Our ability to carry oxygen and thus sustain complex life is intimately tied to the violent deaths of stars. Even our neurons, built from elements created in those cataclysms, enable us to ponder this connection. The constant reprocessing of elements by successive generations of stars underlies galactic chemical evolution. The first generation created some heavy elements and seeded the next. Later stars produced heavier elements such as carbon and magnesium, while supernovae generated elements heavier than iron. Nearly all elements in the human body have travelled through several supernovae, making each of us a tapestry of recycled stardust. Reflect on how many journeys our atoms have taken. Some may have originated near the core of a massive star in the early galaxy, were ejected and drifted for millions of years, then were incorporated into a star system that formed and died again, before being scattered once more. Eventually, after countless cycles, they found their way into the nebula that formed the Sun. From there, they became part of Earth and eventually part of us. The composition of our bodies mirrors the abundance of elements in the universe. We are mostly oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. Hydrogen came directly from the Big Bang, while the other elements were made in stars and distributed by supernovae. This mixture is not arbitrary. It reflects the cosmic processes that produced these elements and made them available for life. We are not only composed of star stuff, we also continuously interact with cosmic remnants. Cosmic rays generated by supernova remnants pass through us, leaving tracks in our DNA. The sunlight that warms us is the steady nuclear fusion of our star. Meteorites that occasionally fall to Earth are fragments of other bodies, containing minerals and isotopes from long-dead stars. The recognition of this connection has deep emotional resonance. To realize that our blood contains iron from an exploded star is to bridge the gap between the vast and the intimate. It invites humility and wonder. Our daily concerns do not diminish this cosmic heritage. They are enriched by it. When we raise a glass of water, we are drinking molecules that once passed through stars. Over time, the proportion of heavy elements in the universe has increased, enabling planets and life to form. Early in cosmic history, low metallicity limited the formation of rocky planets. As supernovae enriched the interstellar medium, the building blocks for terrestrial planets accumulated. By the time the Sun formed, there was enough iron, silicon, and oxygen to create Earth. This enrichment continues today. Our understanding of these processes comes from spectroscopic studies of stars and meteoritic analyses. By measuring isotopic ratios, scientists can trace which types of supernovae contributed to particular elements. The presence of certain short-lived isotopes in meteorites indicates that a nearby supernova occurred just before the solar system formed. This suggests that our own birth was directly influenced by a stellar explosion. In everyday life, we seldom think about such origins, yet they matter deeply. When we gaze at the night sky, we are looking at sources that made our existence possible. The continuum between microcosm and macrocosm is unbroken. Each heartbeat is in rhythm with processes that occur on galactic scales, and our eventual return to the cosmos will continue the cycle. From a philosophical perspective, recognizing ourselves as part of a cosmic cycle can change how we see our place in the world. We are not separate from the universe. We are expressions of it. Our thoughts and feelings are the result of atoms that have danced through stellar furnaces. While individual lives are finite, the atoms and energy that compose us continue to be incorporated into new forms long after we are gone. Appreciating the cosmic origin of our bodies does not diminish the importance of our lives. It enhances it. It suggests that our existence is part of a larger story, one that began billions of years ago and will continue for billions more. The iron that courses through our veins today may one day be part of another being, somewhere in the galaxy or beyond. Our legacy is carried by the very substance of our bodies. This awareness can influence our values. If the atoms that make us were part of countless earlier beings and will be part of countless more, then our connections with other people and with nature take on added significance. The boundaries between self and environment blur. Environmental stewardship and compassion for others become natural extensions of recognizing our shared material heritage. Throughout history, cultures have sensed this connection in myth and metaphor. Stories of beings descending from the stars or returning to them reflect an intuition that we are not separate from the cosmos. Modern science has given these intuitions a factual foundation. We now know that nearly every element in our bodies has traveled through several stars, validating ancient sentiments with empirical evidence. In today's world, this knowledge can foster global solidarity. When we understand that everyone we meet is composed of the same cosmic materials, shaped by the same processes, and destined for the same eventual recycling, differences shrink in importance. We share not only a planet, but a lineage that stretches back to the earliest generations of stars. That shared origin can inspire empathy and cooperation. Ancient and modern perspectives converge in this realization. When early observers recorded supernovae, they were documenting the sources of future life. When we analyze those records and compare them to spectra from distant explosions, we bridge human experiences across time. The story of iron in our blood and calcium in our bones is thus both scientific and cultural, tying us to ancestors who gazed at the same sky. As we transition to stories of starlight recorded across cultures, keep in mind the personal nature of this cosmic heritage. Our connection to supernovae is not abstract, it is embodied. The atoms that make up our hands and hearts were forged in stars and delivered by explosions. With this awareness, we move to explore how human beings have witnessed and interpreted these celestial events throughout history. Cosmic rays not only pass harmlessly through our bodies, they interact with Earth's atmosphere to create showers of secondary particles. These cascades generate muons that penetrate deep underground and even into our cells. While the exposure is low, over geological timescales, cosmic rays may have contributed to genetic mutations, subtly influencing the course of evolution. Our very ability to adapt may owe something to these distant explosions. Some researchers speculate that variations in cosmic ray flux could be linked to climate changes or mass extinctions, though evidence remains tentative. The idea is that supernovae near the solar system might increase cosmic ray exposure, affecting cloud formation or radiation levels on Earth. Whether or not such links hold, they illustrate how interconnected cosmic and terrestrial processes can be. Studying past supernova rates may shed light on Earth's history. Neutrinos, produced in enormous numbers during supernovae, pass through Earth unnoticed. Trillions stream through our bodies every second, ghost-like messengers from distant cataclysms. Occasionally, a neutrino interacts within a detector buried deep in ice or rock, producing a faint flash that signals its passing. These detections confirm our models of stellar collapse and connect us physically to events occurring on the far side of the galaxy. Beyond iron and calcium, our bodies rely on elements like potassium and phosphorus. Potassium regulates nerve impulses, while phosphorus is essential for DNA and energy transfer. These elements were forged in stars and distributed by supernovae, just like iron. Even trace elements, such as iodine in our thyroids and cobalt in vitamin B12, have cosmic origins. Every biochemical pathway echoes the history of stellar nucleosynthesis. Water molecules in our bodies contain hydrogen atoms that date back to the Big Bang and oxygen atoms formed in stars. Some of these water molecules may have formed in interstellar space long before the Earth existed, condensing onto grains of dust and later being delivered to the young planet by comets and asteroids. When we drink a glass of water, we are consuming a mixture of primordial and stellar ingredients. The geology of Earth bears the imprint of cosmic events. Heavy elements like uranium and thorium, created in supernovae, heat the planet's interior through radioactive decay. This internal heat drives plate tectonics, volcanic activity, and the generation of Earth's magnetic field. Thus, the churning of our planet's mantle and the landscapes we inhabit are linked to the death of massive stars. Radioisotopes within our bodies, such as carbon-14 and potassium-40, are replenished by cosmic rays. Cosmic ray interactions in the upper atmosphere create new isotopes that eventually become part of the biosphere. These isotopes allow us to date archaeological and geological samples through radiometric techniques. The accuracy of such methods depends on understanding the flux of cosmic rays over time. Cosmic rays contribute to atmospheric phenomena like auroras by energizing particles trapped in Earth's magnetic field. When the sun's activity declines, galactic cosmic rays become more prevalent and can influence upper atmospheric chemistry. Though subtle, these effects remind us that our planet lives under a constant rain of high-energy particles originating from distant supernovae. Human creativity has long been inspired by stars. Ancient myths often depict humans as descendants of celestial beings. Modern authors and filmmakers draw on supernova imagery to symbolize sudden change and rebirth. Musicians compose symphonies evoking the grandeur of stellar explosions. This creative engagement reflects a deep-seated recognition that the cosmos is part of our story. Our sense of time is shaped by cosmic cycles. Days, months, and years all correspond to motions of Earth around its star and the Moon. Longer cycles, such as precession and Milankovitch cycles, influence climate patterns. When we consider supernovae, we confront timescales even more vast, reminding us that human history occupies only a blink in cosmic chronology. Many religions and spiritual traditions speak of humans as being made of earth and star. Some scriptures describe life as having descended from the heavens, while others anticipate a return to the sky after death. Though these ideas vary widely, they share an intuition of cosmic connectedness. Modern science offers its own narrative of descent, not from gods, but from stars, enriching these traditions with empirical detail. The quest to decode our cosmic ancestry continues. Astronomers are refining measurements of elemental abundances in stars. Geologists are discovering new isotopic clues in ancient rocks. And biologists are exploring how cosmic events might influence evolution. Every new finding tightens the weave between the macrocosm and the microcosm. As we learn more, our identity as stardust becomes ever more vivid. Our senses depend on elements forged in stars. Vision relies on vitamin A, a compound containing carbon, hydrogen, and oxygen, derived from plant pigments. Smell and taste are mediated by receptors in our noses and tongues, many of which incorporate trace metals like zinc and copper to function properly. Even hearing involves calcium ions in the hair cells of our inner ears. Without stellar nucleosynthesis, these sensory experiences would not exist. The taste of salt unites two elements with cosmic origins. Sodium is produced in massive stars through carbon burning, while chlorine forms when argon captures neutrons in certain stellar environments. When we sprinkle salt on food, we engage in a ritual that spans billions of years of nuclear reactions. The pleasure we derive from flavor is thus a direct consequence of processes that unfolded in faraway suns. Some animals navigate using Earth's magnetic field by sensing tiny crystals of magnetite in their bodies. Magnetite contains iron, an element produced in supernovae. These biological compasses are yet another example of life employing cosmic materials for specialized functions. Our own circadian rhythms may also be influenced by light wavelengths shaped by the chemistry of our star and the atmosphere. A reminder that our biology is tuned to cosmic conditions. Long before compasses and GPS, humans navigated by the stars. Polynesian voyagers crossed vast ocean distances using the positions of stars as guides. Desert caravans oriented themselves by the North Star. Such practices required intimate knowledge of the night sky and reinforced cultural ties to the cosmos. Navigational traditions reveal how practical needs intertwine with reverence for the heavens. Romantic imagery often invokes starlight. Lovers stroll under the stars, poets speak of hearts bursting like supernovae, and artists depict embraces against cosmic backgrounds. These metaphors resonate because they blend the personal with the universal. The same stars that guide ships and inform scientists also watch over human relationships, providing a timeless backdrop to our stories. The food we eat is grown in soil enriched by cosmic processes. Plants absorb minerals like iron, magnesium, and potassium from the ground, each element once forged in a star. Photosynthesis uses photons from the sun which itself formed from material enriched by ancient supernovae. Every meal is a communion with the cosmos, combining energy and matter from stellar and planetary histories. Modern technology depends on elements produced in the hearts of stars. Smartphones, computers, and renewable energy devices rely on rare earth metals and heavy elements like tungsten and platinum. These elements are scarce on Earth because they were created in supernovae and neutron star mergers and later separated during the planet's formation. Our ability to build complex tools is another manifestation of our cosmic heritage. Long before modern telescopes and space observatories, humans looked up and watched the sky. In the summer of 1054, Chinese astronomers recorded a star so bright that it was visible even during the day. It shone for nearly a month and then gradually faded. Those records describe a brilliant guest star that marked the death of a massive star. Its remnant is now known as the Crab Nebula. The annals of history from around the world attest to this event. Japanese, Korean, and Arab astronomers also noted the bright star. Chinese observers described its position relative to known stars, writing that it appeared southeast of Zeta Tauri and remained visible for over a year. Indigenous peoples of North America may have memorialized the event in rock art, suggesting a cultural impact far beyond the literate societies of Asia and the Middle East. Through these stories, we see that the awe inspired by a sudden new star transcends time and culture. Ancient observers did not know the physics of supernovae, yet they recognized the significance of such events. They recorded them with meticulous care, enabling modern astronomers to identify the remnants centuries later. The bridging of ancient texts with modern observations illustrates the continuity of human curiosity. Today, astrophysicists decode the language of starlight, using instruments far more sensitive than the naked eye. Spectrographs break light into its component colors, revealing the fingerprints of elements. When a supernova explodes, its light carries information about the progenitor star and the nature of the explosion. By comparing modern data with historical accounts, scientists piece together the story of a star's death across millennia. The Crab Nebula stands as a testament to this union of old and new knowledge. The nebula's filaments and glowing gas tell of a core collapse supernova. The pulsar at its center is the leftover neutron star, spinning rapidly and emitting beams of radiation. Without the writings of 1054, it would be harder to link this nebula to a specific date and event. With them, the connection is clear and personal. Beyond the Crab Nebula, other supernovae have been chronicled by ancient observers. In 1006, a brilliant star appeared in the constellation Lupus, shining brighter than Venus. In 1572 and 1604, Tycho Brahe and Johannes Kepler documented stars that flared up unexpectedly. Each time, the event challenged prevailing notions of an unchanging sky and helped pave the way for modern astronomy by showing that the heavens are dynamic. The term nova, meaning new, reflects the surprise these stars inspired. For centuries, philosophers and theologians debated their significance. Were they omens, divine messages, or natural phenomena? While interpretations varied, the underlying sense of wonder was universal. The night sky served as a canvas for stories, myths, and scientific inquiry alike, connecting communities across continents and ages. In the present era, supernovae continue to captivate. When a nearby star detonates, it becomes one of the brightest objects in the sky. Observatories around the world rush to capture its light across the electromagnetic spectrum. Citizen scientists contribute by pointing small telescopes toward the event, joining a lineage of watchers that stretches back millennia. Modern stories also involve distant galaxies. When a Type Ia supernova occurs in a faraway spiral, its brightness allows astronomers to measure cosmic distances with remarkable precision. These measurements were key to discovering the accelerating expansion of the universe. Thus, supernovae not only inspire wonder, but also inform cosmology, serving as markers on the cosmic ladder that connect our local experiences to the grand scale. The language we use to describe supernovae blends poetry with physics. Terms like cosmic fireworks and stellar death convey the drama, while technical phrases like thermonuclear runaway and shock breakout explain the mechanisms. This dual language echoes the dual nature of our relationship with the cosmos. We are both emotional beings, moved by beauty, and rational minds driven to understand. Throughout history, different cultures have given names to stars and created stories around them. These names reflect local languages and cosmologies, yet they often refer to the same objects. A supernova, recorded in China, may have been noted by an Arabic astrologer and later remembered in European folklore. Such cross-cultural links underscore the shared human experience of watching the sky. In literature and art, supernovae serve as metaphors for transformation. Writers describe emotional upheavals as being like exploding stars. Artists paint swirling nebulae, capturing the interplay of chaos and beauty. These creative works show that the influence of supernovae extends beyond science into the realm of human expression, providing a language for articulating change, loss, and renewal. The digital age has expanded the community of skywatchers. News of a new supernova travels quickly across social media. Amateur astronomers share images and measurements online, and professional observatories coordinate follow-up observations. Students in classrooms thousands of miles apart can participate in real-time observations, turning the detection of a distant explosion into a shared educational moment. Ancient records are now treated as data. Scholars translate and analyze historical documents, aligning dates with modern calendar systems and matching descriptions with celestial coordinates. By combining textual scholarship with astrophysics, researchers extract quantitative information from qualitative descriptions. The resulting chronology enhances our understanding of past events and demonstrates the value of preserving cultural heritage. The interplay between memory and measurement enriches both science and humanities. A footnote in a centuries-old chronicle becomes a data point in a modern database. The arcs of meaning stretch from mythic narratives to numerical fits. This synthesis demonstrates that knowledge is cumulative and collaborative, bridging disciplines and generations in pursuit of understanding. When we read that a guest star was seen near a particular constellation, we feel a kinship with those long-ago observers. They too looked up and asked what the appearance meant. Today, we may answer that question with physics, but the underlying curiosity remains the same. Supernovae thus serve as a thread connecting us to our ancestors. The universality of this fascination can foster global solidarity. People in different parts of the world may see the same supernova and discuss it in online forums. Language barriers fall away in the face of shared wonder. Through these conversations, we build a sense of belonging to a single planetary community under a vast and dynamic sky. Supernovae are also cosmic yardsticks. Type 1. A supernovae explode with a consistent, intrinsic brightness, making them reliable standard candles. By comparing their apparent brightness to their known luminosity, astronomers calculate distances across billions of light years. This method was crucial in discovering dark energy and continues to refine measurements of the universe's expansion. As we recount stories written in starlight, we recognize that narrative is a powerful tool. The tales of exploding stars weave together scientific data, cultural memory, and personal experience. They inspire budding astronomers, artists, and storytellers alike. The enduring wonder of supernovae lies not only in their brilliance, but in the way they link us across time and culture. As we transition from stories of observation to the cycles that supernovae drive, we carry with us threads of awe and inquiry. The next reflections will explore how explosions lead to new beginnings, continuing the cycle without end. Before we turn to that theme, remember that the narratives we build are as much a part of the cosmos as the events themselves. By telling stories of the stars, we become part of their legacy. In 1987, a supernova exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Known as SN 1987A, it was the brightest supernova seen from Earth since Kepler's star. Observers across the southern hemisphere watched it with naked eyes and telescopes. For many, it was a once-in-a-lifetime event that brought the study of stellar death into living memory. SN 1987A was also the first supernova from which neutrinos were detected directly. A handful of neutrino detectors around the world recorded a burst of neutrinos hours before the light reached Earth. This confirmed theoretical predictions that most of a supernova's energy is carried away by neutrinos. It also inaugurated the era of multi-messenger astronomy, where different types of signals are combined to tell a fuller story. A new window into supernovae is opening with gravitational wave astronomy. Though no gravitational waves from a core collapse supernova have yet been detected, models predict that asymmetries in the explosion could generate detectable ripples in spacetime. Future detectors may record such signals, providing information about the internal dynamics of the collapsing star that cannot be gleaned from light alone. Neutrino and gravitational wave observatories rely on global cooperation. Experiments like IceCube at the South Pole and Super Kamiokande in Japan monitor for neutrino bursts, while LIGO and Virgo listen for gravitational waves. When a supernova occurs, alerts are sent across networks so that optical, radio, and X-ray telescopes can observe the event. This coordinated response exemplifies the collaborative nature of modern astronomy. In our own galaxy, no bright supernova has been seen since 1604, although there have been numerous fainter events. The absence of a nearby supernova in recent centuries means that few people alive today have experienced the awe of a star exploding in the Milky Way. Yet astrophysicists estimate that a core collapse supernova should occur in our galaxy roughly every 50 years. We are overdue for a spectacular visitor. Anticipation of the next galactic supernova is palpable among astronomers. Instruments are ready to detect the earliest signs, whether in neutrinos, gravitational waves, or light. Amateur observers check known supernova candidates, while professionals monitor the red supergiant Betelgeuse for signs of impending collapse. When the next supernova comes, it will be a global event, connecting communities in real time. Large-scale surveys have revolutionized the study of supernovae. Automated telescopes scan the sky nightly, using software to detect transient objects. Catalogues of thousands of supernovae allow researchers to study populations statistically, revealing trends in their brightness, host galaxies, and environments. These surveys also increase the chance of catching unusual events, like superluminous supernovae and failed explosions. Classification schemes help astronomers organize the diversity of supernovae. Type Ia explosions are thermonuclear and lack hydrogen lines in their spectra, while Type Yi supernovae show hydrogen lines and result from core collapse. Subtypes like Ib and Ic reflect the stripping of the outer layers of the progenitor star. These categories guide our understanding of progenitor systems and their evolutionary paths. Many cultures interpret the sudden appearance of a bright star as a symbol of change. In East Asia, guest stars were sometimes seen as omens of dynastic shifts. In Europe, the supernova of 1572 challenged Aristotelian cosmology and catalyzed scientific revolutions. Indigenous narratives often weave these events into origin stories. The same celestial phenomenon thus acquires different meanings in different contexts. As we contemplate the stories written in starlight, we recognize that our interpretations evolve. What was once a portent becomes a data point. What was once a myth becomes a metaphor. Yet the sense of wonder remains. By combining ancient accounts with modern techniques, we honor both the curiosity of our ancestors and the rigor of contemporary science. This dual approach enriches our understanding of the cosmos. Radio observations reveal the aftermath of stellar explosions in rich detail. Supernova remnants emit synchrotron radiation as electrons spiral around magnetic field lines, producing bright radio shells. By mapping these emissions, astronomers can infer the geometry of the remnant, the strength of magnetic fields, and the distribution of accelerated particles. Radio waves penetrate dust, allowing us to study events hidden at optical wavelengths. In X-rays and gamma rays, supernova remnants glow with high-energy processes. Hot gas, heated to millions of degrees by shock waves, emits X-rays, while radioactive isotopes, created in the explosion, produce characteristic gamma-ray lines as they decay. Observatories like Chandra, XMM Newton, and Fermi monitor these wavelengths, providing insights into the physics of shock heating and nucleosynthesis. Each energy band reveals a different aspect of the explosion. Fast radio bursts, mysterious millisecond flashes of radio waves, may be linked to magnetars, highly magnetized neutron stars formed in supernovae. Though their origins remain uncertain, some FRBS are associated with galaxies where recent star formation suggests a population of young neutron stars. If these bursts are connected to supernova remnants, they add another layer to the rich phenomenology of stellar death. Gamma-ray spectroscopy allows astronomers to observe specific radioactive isotopes produced in supernovae. Emission lines from decay of nickel-56, titanium-44, and other nuclides provide direct evidence of nucleosynthesis. By measuring these lines, scientists determine the amount of material produced and test models of explosive burning. Such observations connect theoretical calculations to the real chemical output of supernovae. Supernovae inspire interdisciplinary collaborations between scientists and artists. Composers write symphonies that mirror the crescendo and sudden silence of a star's demise. Visual artists create installations that use light and shadow to evoke shockwaves and nebulae. Dancers choreograph movements inspired by collapse and expansion. These works translate astrophysical concepts into human experience, making the science accessible through emotion and creativity. The band of light, called the Milky Way, has inspired myths and guides. Some cultures see it as a river of souls, others as a road for deities. When a supernova appears along this band, it stands out against the familiar glow, prompting stories and records. The Milky Way itself is a composite of billions of stars, each with its own cycle of life and death, yet together forming a continuous thread across the sky. Historic supernovae were sometimes used as chronological markers. Chinese court records mention the appearance of guest stars in specific years, anchoring historical events. Medieval chroniclers linked the appearance of bright stars to the reigns of kings. These associations reflect both the awe induced by celestial events and the human desire to weave cosmic phenomena into the fabric of earthly history. In the early universe, hydrogen and helium dominated, and heavy elements were scarce. It was only through nucleosynthesis inside stars and the dispersal of these elements through supernova explosions that complexity arose. The cycle of matter begins with the gravitational collapse of a gas cloud, proceeds through the life and death of stars, and returns to the interstellar medium in enriched form. This cycle sets the stage for everything else. When a star like the Sun dies, it sheds its outer layers gently, creating a planetary nebula. But massive stars end their lives violently. The core collapses, the outer layers rebound, and a supernova occurs. The core may become a neutron star or a black hole, while the expelled material forms a supernova remnant rich in heavy elements. Over time, these heavy elements mix with pristine gas, altering its composition. When a new cloud collapses under gravity, the presence of metals allows it to cool more efficiently and fragment into smaller pieces, forming a variety of stars. Some of these stars will live long, quiet lives. Others will be massive and short-lived. Each will eventually return material to space, continuing the cycle. The phrase "circle without end" encapsulates this process. There is no final destination for matter. It flows from one form to another. The atoms that once resided in a star may become part of a planet, then part of a living organism, then again, part of a cloud. The universe is a continuous recycler, with supernovae acting as one of the chief engines of transformation. Galactic chemical evolution models show that the abundance of heavy elements rises over time through successive star formation and supernova explosions. This gradual enrichment influences the types of stars that form and the potential for planetary systems. Life as we know it requires a certain concentration of elements like carbon, oxygen, and iron. Without repeated cycles of destruction and creation, these elements would remain locked in stellar cores. The R process and silicon burning processes in supernovae create elements heavier than iron, such as gold and uranium. These elements are rare and dispersed across the galaxy. When a region of gas and dust collapses, only trace amounts are incorporated into new stars and planets. Yet these traces become significant. The gold used in jewelry and electronics, the uranium used in reactors, all owe their existence to this cosmic recycling. The cycle also encompasses energy. Particles accelerated by supernova remnants eventually lose energy and become part of the galactic cosmic ray population. They may be captured by magnetic fields, interact with gas, and contribute to the heating and ionization of clouds. In this way, the energy from explosions persists, influencing the next cycle of star formation in subtle ways. Shock waves from supernovae can compress gas clouds, initiating collapse. Conversely, they can disrupt clouds, halting star formation. The balance depends on the density and structure of the gas, making the cycle dynamic and unpredictable. Even when an explosion triggers new stars, those stars may eventually produce their own supernovae, continuing the cascade. On human timescales, these cycles are imperceptibly slow. Tens of millions of years may pass between the ejection of material from a star and its incorporation into a new star. Yet on cosmic timescales, the cycle is continuous and unending. There is no start or finish, only a flow. When we look at star clusters of varying ages, we see snapshots of this process at different stages. Our own solar system fits into this circle. Evidence from meteorites points to a nearby supernova just before the Sun formed. The shockwave may have compressed the protosolar nebula, and the injected isotopes served as heat sources as planetesimals formed. Without that event, our system might not exist. Thus, our planet is a product of the cycle, and we are participants in it. The concept of an endless circle has deep resonances in myth and philosophy. Many cultures have stories of cycles: birth, death, and rebirth, seasons, life emerging from death. These stories mirror the physical processes we observe in the cosmos. The stars themselves live and die, but the matter they shed gives rise to new generations. In both human thought and astrophysics, cycles provide a framework for understanding change. Recognizing the circle without end can offer comfort. It suggests that endings are also beginnings, that loss is followed by renewal. In the cosmic context, nothing is wasted. Even the most violent event leads to new possibilities. This perspective can inform how we view our own lives and the world, encouraging us to see continuity amidst change. Dust grains play a crucial role in the cycle. Formed in the envelopes of dying stars and in supernova ejecta, dust seeds the formation of planets. These tiny particles carry refractory elements, like silicon and carbon. As they drift through space and become incorporated into new protoplanetary disks, they provide the scaffolding on which solids assemble and worlds eventually emerge. The fates of massive stars include more than supernovae. In some cases, the core collapses directly into a black hole without producing a bright explosion. In others, a gamma-ray burst accompanies the supernova, releasing a narrow beam of high-energy radiation. The compact remnants, neutron stars and black holes, are endpoints of the nuclear burning cycle, but they are also sources of gravitational waves and relativistic jets that influence their surroundings. Cosmic rays, neutrinos, and photons all play their part in the cycle. Neutrinos escape, almost unimpeded, from a collapsing core, carrying away a significant fraction of the gravitational energy. These ghostly particles stream through space and even through our bodies, faint whispers of distant cataclysms. Their detection on Earth provides insights into the processes deep within stars. In star clusters, we see the cycle at different phases side by side. Young clusters contain massive, blue stars that will explode in a few million years. Older clusters are populated by long-lived, lower-mass stars that will persist for billions of years. The juxtaposition reminds us that within a single region of space, many cycles unfold simultaneously, each star on its own timeline, yet linked to the same cosmic reservoir. The interplay between cosmic cycles and human cycles is profound. While our lives are brief compared to the lifetimes of stars, we partake in the same flow of matter. Our bodies are temporary configurations of atoms that have traveled through countless stars. When we die, those atoms will return to the environment, eventually to be reassembled into new forms. Our personal cycles mirror the cosmic cycle. This perspective can affect how we value our experiences. Knowing that our joys and sorrows are part of a larger pattern can bring a sense of meaning. We are not isolated. We are expressions of a universe that constantly renews itself. Even in times of loss, we can find solace in the knowledge that nothing is truly lost, only transformed. As we examine the circle without end, we also acknowledge the role of randomness. The particular paths of atoms, the timing of supernovae, and the formation of planets depend on chance interactions. Yet from this randomness emerges order and structure. The galaxy is shaped by both deterministic laws and stochastic events, and our existence is the outcome of countless contingencies within the cycle. In moving from cycles to reflections on legacy and impermanence, we carry with us the understanding that change is the only constant. The circle without end does not diminish the uniqueness of any moment. Rather, it enriches it. Each stage of the cycle has its own beauty and significance, and by appreciating the flow, we become attuned to both the continuity and the novelty of cosmic evolution. Organic molecules discovered in interstellar clouds hint at the complexity arising within the cycle. Molecules like formaldehyde, methanol, and even amino acids form on dust grains in cold molecular clouds. These prebiotic compounds are later incorporated into comets and asteroids, which deliver them to young planets. Life's ingredients thus travel through the cosmic recycling system long before biology emerges. Planets themselves participate in the cycle. Some are born, harbour life, and then are destroyed by stellar evolution or collisions. Debris from shattered worlds can coalesce into new bodies or be accreted onto existing ones. The fate of any given planet depends on a multitude of factors, but all are ultimately subject to the processes that govern the flow of matter in the galaxy. Star formation is also influenced by large-scale structures like spiral arms. As gas enters a spiral arm, it is compressed, forming stars. The subsequent supernovae then inject energy and metals back into the interstellar medium, which are carried downstream by the galactic rotation. This spiral arm traffic pattern contributes to the distribution of star clusters and the cycling of material around the galactic disk. Cosmic rays may even influence Earth's weather. Some theories propose that high-energy particles can promote cloud formation by ionizing atmospheric molecules, although the extent of the effect is debated. If true, changes in cosmic ray flux due to nearby supernovae could have subtle climatic impacts. Research into these connections exemplifies the interplay between cosmic events and terrestrial phenomena. The concept of cycles is not limited to the cosmos. On Earth, water cycles between ocean, atmosphere, and land. Nutrients cycle through ecosystems. Economies experience boom and bust. By drawing analogies between these processes and the cosmic cycle, we gain a deeper appreciation of the universality of transformation. Patterns repeat at different scales, linking the global to the galactic. Cultural traditions often reflect cyclical thinking. Eastern philosophies emphasize reincarnation and the turning of the wheel, while indigenous cultures speak of seasons of creation and destruction. These narratives resonate with the astrophysical reality of matter cycling through stars and space. The language differs, but the underlying recognition of continuity amidst change is shared. Time itself is perceived differently in light of cosmic cycles. Geological epochs, measured in millions of years, suddenly seem brief compared to stellar lifetimes. Human generations are fleeting. Yet our minds can comprehend cosmic timescales, and this ability to stretch our temporal perspective enriches our sense of belonging in the universe. We are present for only a moment, but that moment is part of a vast continuum. The ultimate fate of matter is still a topic of speculation. Some theories suggest that protons may eventually decay, turning matter into radiation. Others propose that black holes will evaporate through Hawking radiation, releasing their contents. In cyclic cosmological models, the universe itself may undergo endless cycles of expansion and contraction. Whatever the outcome, the idea of perpetual transformation persists. Cycles also feature in cosmological myths. Ancient Hindu texts describe the universe as going through cycles of creation and destruction lasting billions of years. Stoic philosophers imagined conflagrations that reset the cosmos. Modern cosmologists explore cyclic models where the Big Bang is followed by a big bounce. These ideas differ in detail, but share a recognition that creation and destruction are intertwined. Understanding cycles encourages us to embrace change in our own lives. Just as stars must die to create the elements necessary for life, we must accept endings to enable new beginnings. Loss and renewal are part of the same process. By seeing ourselves within a larger cycle, we gain resilience and hope. We learn to trust in the ebb and flow of existence. Energy also cycles in the cosmos. Gravitational potential energy in gas clouds is converted into kinetic energy as they collapse, then into thermal and radiant energy in stars. Supernovae release stored nuclear energy, driving shocks that heat and stir surrounding gas. Over vast timescales, energy is redistributed through radiation, winds, and cosmic rays, eventually dissipating as the universe expands. The flow of energy parallels the flow of matter. The cosmic microwave background, CMB, is a relic of an early phase of the universe's cycle. This faint afterglow of the Big Bang fills space with photons that have been cooling for nearly 14 billion years. While not directly linked to supernovae, the CMB provides a backdrop against which the baryon cycle unfolds. Its uniformity and slight ripples set initial conditions for the formation of stars and galaxies. Cosmic expansion influences the recycling of matter. As the universe expands, galaxies move farther apart, reducing the rate at which they merge and interact. This affects how often gas is compressed into stars and how efficiently supernovae return material to the intergalactic medium. The discovery that the expansion is accelerating adds a new twist to the cycle, raising questions about the ultimate fate of matter. The large-scale structure of the universe resembles a cosmic web of filaments and nodes. Galaxies form along these filaments, with clusters at their intersections. Gas flows along the web, feeding galaxies, while feedback from supernovae and black holes blows gas back into the voids. The pattern of material moving through this network is another manifestation of cycles, playing out on scales much larger than individual galaxies. Star formation rates rise and fall over cosmic time in quasi-periodic bursts. After a galaxy experiences a surge of star formation, supernova feedback and gas consumption lead to a lull. Later, inflows of fresh gas can spark another burst. These star formation cycles contribute to the diversity of galaxy properties we observe and highlight the importance of temporal patterns in cosmic evolution. Angular momentum cycles through stellar systems. Stars inherit spin from the clouds that birth them, but they also lose angular momentum through stellar winds and mass ejections. In binary systems, mass transfer can spin up or spin down companion stars. Supernova explosions can impart kicks that send neutron stars whirling across the galaxy. The exchange of angular momentum is another subtle cycle connecting stars and space. Cycles also occur in multi-star systems through recurring novae. When a white dwarf in a binary system accretes hydrogen from a companion, the material can ignite explosively on its surface, producing a nova. This process can repeat many times, with each outburst returning material to space. Such cyclical eruptions illustrate that not all stellar explosions are one-time events. Some stars live through repeated flare-ups before their final demise. As we near the end of this reflection, the tone shifts towards synthesis and contemplation. We have journeyed from the explosive deaths of stars to the shaping of galaxies, from the forging of elements to the making of our own bodies, from ancient chronicles to modern science. Throughout, a thread of continuity and wonder has woven the narrative together. Now we dwell on what this means for us. The legacy of supernovae is vast. It is written in the metallicity of galaxies, the diversity of stars, the existence of planets, and the chemistry of life. It is etched into stone by ancient observers and recorded in the spectra captured by contemporary instruments. This legacy is not static. It continues to unfold. Each new supernova adds to the richness of the story, and each generation of humans interprets it anew. Impermanence is a recurring theme. Stars that burn brightly must one day fade or explode. Galaxies that form stars vigorously will eventually exhaust their gas. Even the elements themselves are subject to transformation, combining into molecules, being locked in rocks, entering living organisms, and being returned to space. Nothing in the universe is permanent, yet everything contributes to an enduring tapestry. This impermanence is not cause for despair. It is a source of beauty. The fleeting brilliance of a supernova is striking precisely because it is brief. The cycle of matter through stars and space adds depth to the cosmos. Our awareness of this cycle allows us to appreciate the here and now. We know that the moment we witness a meteor streak across the sky is part of a process billions of years in the making. Beauty is found not just in the spectacular, but in the subtle. The glow of a nebula, the faint shimmer of a star cluster, the chemical composition of a grain of dust, all carry beauty when seen through the lens of understanding. When we realize that the calcium in our bones links us to a long-dead star, we find beauty in our own physical makeup. Knowledge enriches perception and deepens appreciation. The narrative of exploding stars offers a model for embracing change. Supernovae show that endings are necessary for new beginnings. They teach us that destruction can be creative, that letting go can make room for growth. This lesson can apply to personal journeys and societal transformations. Nature's cycles provide metaphors and frameworks for navigating change with grace. In a practical sense, the study of supernovae has tangible benefits. By measuring their brightness and understanding their physics, we have mapped the expansion of the universe and discovered dark energy. By tracing the elements they produce, we have learned about the conditions necessary for life. By analyzing cosmic rays, we have gained insights into particle acceleration. The emotional resonance of supernovae is matched by their scientific significance. Looking forward, future telescopes will deepen our understanding. The next generation of observatories will detect supernovae in the earliest galaxies, revealing how the first explosions influenced cosmic dawn. They will map the distribution of heavy elements across the universe, showing where life might arise. They will capture neutrinos and gravitational waves from exploding stars, adding new dimensions to our sensory palette. The story continues. At the individual level, learning about supernovae can inspire reflection. When we go outside at night and look up, we may see stars and think of their fates. We may imagine the atoms in our bodies returning to space, joining the cosmic cycle once more. This perspective can foster a sense of connectedness with the universe and with each other. We are all made of the same matter. We are all part of the same story. Gratitude is an emotion that emerges from contemplating our cosmic origins, recognizing that our bodies and world are gifts of countless stellar generations, can foster a deep appreciation for life. This gratitude encourages us to cherish our time, care for our planet, and respect the interconnectedness of all things. It reminds us that the universe is not indifferent to us. It is literally within us. As we look ahead, we acknowledge that the journey of discovery is ongoing. New instruments and ideas will challenge our understanding, and unexpected phenomena will expand our horizons. By remaining curious and open, we honor the legacy of those who first looked up and wondered. The next part of our story will continue to weave science and wonder, inviting us to explore the cosmos, both outward and inward. Art and culture thrive on cosmic metaphors. Painters use nebulae as backdrops. Filmmakers set love stories against star fields. And poets liken emotions to tidal forces and supernovae. These creative expressions translate scientific ideas into sensory experiences. They allow us to feel the scale and beauty of the universe in human terms, reinforcing the connection between knowledge and imagination. The boundary between knowledge and mystery is where curiosity flourishes. For every question that science answers about supernovae, new questions arise about their nuances. Mystery is not a barrier to understanding, but a driver of inquiry. Embracing the unknown keeps our minds flexible and our hearts open to wonder, ensuring that the pursuit of knowledge remains a living, breathing process. Learning about the cosmos is itself cyclical. Discoveries build upon previous work, and paradigm shifts often return to refine earlier ideas. Theories are born, tested, revised, and sometimes discarded, only to inspire new lines of thought. This iterative process mirrors the cycles we observe in nature: creation, transformation, and renewal. Recognizing this pattern encourages patience and perseverance in the face of uncertainty. Wonder is a renewable resource. Every time we learn something new about the universe, it opens a door to further amazement. This replenishing cycle of knowledge and awe sustains scientific endeavors and artistic inspiration. It keeps our curiosity alive, inviting us to continue exploring not because we lack answers, but because each answer reveals deeper layers of beauty. By nurturing wonder, we honor the legacy of exploding stars and the cosmos they illuminate. Reflection on our cosmic heritage naturally leads to questions about responsibility. If our atoms carry the history of the universe, then our actions contribute to its future story. We become stewards of stardust, shaping how it will be used and transformed. This sense of responsibility can guide us to make choices that honor the past and nurture the future. Humility arises naturally from the cosmic perspective. When we understand that our bodies are composed of atoms forged in stars, and that our planet is a speck in a vast galaxy, our personal concerns take on a different scale. This does not trivialize our experiences. Rather, it situates them within a larger framework. Recognizing our smallness can foster compassion, gratitude, and a sense of responsibility toward one another and our world. The interplay of scientific discovery and personal meaning is a hallmark of modern culture. Facts about supernovae and galaxies are not just abstract. They inform poetry, philosophy, and ethics. Discoveries about the age of the universe influence our concept of time. Insights into cosmic cycles inspire metaphors for personal growth. The boundary between scientific knowledge and human wisdom is porous. Hope can be found in the resilience of cosmic cycles. The universe has endured cataclysms and yet produces beauty again and again. Star clusters dissolve, but new ones form. Galaxies collide, but new structures emerge. On Earth, ecosystems recover from disturbances, and societies rebuild after crises. The pattern of recovery woven into the cosmos encourages us to believe in renewal at all scales. Our destiny as a species may one day involve carrying our stardust heritage beyond Earth. If humans venture to other planets or star systems, we will bring with us the atoms forged in ancient supernovae. In doing so, we will extend the reach of those elements to new environments, continuing the cycle in another form. The story of supernova legacy thus becomes part of the story of exploration. As this part of the documentary draws to a close, we reflect on the synergy between wonder and inquiry. We have explored facts and feelings, data and stories, cosmic distances and personal connections. This blend is essential for a full appreciation of the universe. Knowledge satisfies curiosity, while wonder keeps curiosity alive. Together they motivate continued exploration. We end not with finality, but with anticipation. The threads we have woven about stars, cycles, and connections will continue in the next part. There, we will delve deeper into the mysteries that remain, perhaps exploring other cosmic phenomena or tracing new lines of influence. Until then, we carry with us a sense of belonging to something vast, dynamic, and beautiful, and an invitation to keep looking up. As a final reflection in this part of our journey, consider the interplay of legacy, impermanence, and beauty. Legacy speaks to the accumulation of events and their lasting impact. Impermanence reminds us that change is inevitable and that endings are integral to beginnings. Beauty emerges when we see these truths together, appreciating the transient nature of phenomena and the enduring patterns they create. We end this part not with a conclusion, but with an invitation to continue exploring, to keep asking questions, and to remain open to wonder. New discoveries await, and new connections between the cosmos and our lives will be revealed. The next part of our documentary will carry forward the threads we have woven here, integrating them into an even larger tapestry of cosmic understanding.